But they can ping me, but I'll be. Oh, listen, my email address and my website is on there. Contact me with any questions you have. I also have a bunch of. I have unique resources on my website, so if you guys are in our website, it's really cool. It's bright pink. The cursor is also sparkles. Absolutely, please. And if you guys have any questions about being in grad school or academia or whatever, happy to talk. Email me. I'm reachable. Of course.
Oh.
Of course.
Thank you.
Of course. Just take the little parts, you can throw out my name, don't worry about it. Ready for this, right? Oh my gosh. I'm. Oh, girl. Whatever. What is it's what up now? Yeah, I've got mine before I have to figure out safety. Oh, mine is.
He said, "About actually."
Yeah. Yeah, I have it for different age levels. So if one is access. Same become period exactly. So exactly. Happy hours on the president, you know. If it's not from the audience, it's fantastic question. So,
Okay. We're going to get started. I think we have folks on the phone now as well, online now as well. Great. And we have the crew here at Goddard. So let me welcome you all to Goddard. This crew got to go on a tour. We'll talk a little bit about some of the things you saw. I'm just going to give you the, my current version of what I'm excited about in ISAM right now. And of course, with a bend towards what's happening here since we're at Goddard. So you're at Goddard Space Flight Center, where a lot of satellite servicing activities have happened through the years. The Hubble Space Telescope being the kind of flagship of it, still operating after 5 servicing missions. And we just learned about habitable worlds and about how the instruments, of course, are the most important thing. And that's why they call it the payload. It pays the bills. Hubble, everybody knows, was rescued. What people sometimes don't realize is the reason Hubble was rescued and serviced so many times is because we also put new instruments in it almost every time we went up. And those instruments made it a world-class observatory every time that happened. So, so when we talk about satellite servicing, at least for here, the priority, my biggest goal is to enable future observatories and other assets to have their payloads be upgraded so that we're launching massive things. The Hab Worlds telescope is massive, and we can keep using that incredible asset by putting new instruments in it and advancing new science. And by the way, I think Hubble, there was a Nobel Prize from Hubble. It was from an instrument that did not launch with Hubble. So what I always say is I want to be the scientist that launches the instrument that gets put in later, because that's the one that's winning the Nobel Prize. Okay, this is a picture of the lab that some of you all saw. That's an image from OSAM-1 testing that happened here. So you all hopefully have heard about OSAM-1. That mission's canceled, but great work happened there, and we're working to apply it towards other future things. If you go to the next chart, I'll just show you some other things that are happening. On the left, actually, the Catalyst crew is here with their Link spacecraft right now. They're in the thermal vac chamber. Unfortunately, the doors were closed and you guys couldn't see that spacecraft. But I'll tell you, that little thing packs a mean punch. It's launching in 2026, exclamation point. That's 9 months after we got them on contract. So extremely fast and daring mission there to go save the Swift spacecraft. Very excited about that. On the right, I have this mission called Fly Foundational Robots, which will launch in 2027. It's a low Earth orbit polar demonstrator of this 7-DOF inchworming capable robot arm. You see it there holding an ORU, an orbital replacement unit. Some people call a line replacement unit. Some people call it an instrument module. Some people call it other things, right? And so this is will be a great demonstration in 27. And Goddard, it has a guest roboticist program. Goddard is the team that was doing all the robotics that you just saw are working as the first guest roboticist on that and helping develop the interfaces to do that. And very soon you will see more information about how you guys can, if you have robot tasks you want to do with this, can apply into a prize challenge approach to win time to operate the robot on this and get data from it. So very, very exciting. Of course, an extremely inexpensive mission. Hopefully it will work. We don't know how long it will work for. It's not going to be the thing that solves all our problems. We're going to solve our problems by lots of incremental steps. And so I'm excited, very excited about this incremental step that gets us to, some of those future things. Next chart. You also probably know about the RSGS mission. So this is DARPA's Robotic Servicing Geosynchronous Satellites mission. DARPA, Northrop Grumman Space Logistics, Naval Lab, US NRL, and Goddard. Goddard's supporting also. So NASA is supporting through an interagency agreement with DARPA, and some of the folks here are working the robotics and the simulation of those robotics and other things in support of that, launching also this year. Exciting. Next chart. I think I put a Roman chart in here, right? Yeah, so you guys were, some of you, actually, the folks in the room were really lucky. When they were walking by the clean room that Roman is sitting in right now, they opened up the roll-up door to move something in, which has almost never happened. And so they got a great view in of that telescope, which was fortunate because the main viewing area is currently blocked off because 60 Minutes is filming a special on it. So we're all very excited about Roman. Those two pictures on the left are Roman at facilities at Goddard. I wanted to just mention that Roman is serviceable. And we did get some features added to Roman, a hemispherical retroreflector, which increases the range of a LiDAR. So when you're doing prox ops, it makes it so you can pick it up from a further range. April tag fiducials, proximity operations fiducials placed, kind of wherever we could fit them that made sense. But so that we could use it for a final approach. There's a flight releasable grapple fixture, which is a huge deal. Doing capture is hard, so that makes it actually quite a bit easier. And then this bottom right picture, you can't really see anything, but trust me, those are robot-friendly refueling interfaces, so that a robot could open up where that fill and drain valve is and do some refueling if Roman ends up needing it. So these are kind of, baby steps in the serviceability. Hubble was fully serviceable. James Webb was not serviceable. Roman is kind of minimally serviceable, and hopefully next chart, Hab Worlds will be, as we discussed, completely serviceable again. Similarly to how Hubble was serviced, although we're exploring the trade space, there's a lot of work to go to figure out what this telescope looks like. There's a lot more work to go. No, there's not more work to go. There's also a little bit of work to go to figure out how to make it serviceable. Make no mistake, the telescope is the hard part. The servicing is actually kind of not that hard. But adding servicing to such a complicated thing is certainly a challenge, and we're working with them now to understand how we might do that. So next chart. What else are we doing here at Goddard? Well, I always, when I talk about ISAM and NASA, I always put this picture up, and actually usually there's a movie that shows the assembly of space station happening. But so this picture is from 3 days ago. This web page down here you can go to and get a picture of the current configuration of space station. It's just been amazing to see how that picture changes. 1, 2, 3, 4, 5 visiting vehicles there right now. Including Crew Dragon, a commercial supply vehicle, Cygnus, a commercial supply vehicle. So how do we do satellite servicing in the future? We have to have commercial industry providing these services for us, and we're working really hard towards that. And you saw that in the Catalyst and Motive products on that first chart. Commercial companies building COTS products to make it affordable. Also, I put a note up there, AMS repair. The Goddard tools team from Hubble has been very much involved in alpha magnetic spectrometer, which is an instrument that I think you can't actually see. It's on the zenith face. Maybe you can see a corner of it up there. But those tools there's another repair that's about to happen, astronaut base repair, and those tools for that repair were built here and just recently shipped, I think. Next chart. Okay, so, and of course, Goddard, we also are very, very proud to be the, actually, good. There was a skip there. Yeah, you leave it here. Yeah, okay, so ignition just happened. It's very recent. You all know about Orion and Human Landing System. The HLS systems are all, using lots of refueling and in-space servicing type capabilities. We don't know yet what Space Reactor 1 or Moonbase will use in terms of ISAM capabilities, but it's ripe, very ripe for these technologies. Space Reactor 1, I show a picture on the bottom right there of an older concept for a nuclear electric propulsion system to go to Mars. That's a nuclear reactor on the end and thrusters on the back end. It's burning xenon, lots and lots of xenon, so probably not all launchable together. Those radiators are the size of the space station solar array, and they're using a 500 Kelvin coolant. Okay, this is one concept for how it would work, I should say. But so there's some really, really hard challenges there that I think in space servicing, in space assembly helps us solve. And so it'll be interesting to see as we go forward with that. And also as we go forward with a more permanent moon base, how do we maintain these systems? How do we make them interoperable? How do we have common interfaces for things like batteries or computers or smoke detectors or whatever that get plugged in on all these things? And so some interesting stuff coming there, and stay tuned. We'll all learn together what that ends up looking like. So exciting things going on. I think I'm really glad that you guys are all in this field. We need you badly. We need your youth. We need your innovation. We need your excitement. So keep pushing. And on the next chart, you all know about Cosmic. You're here for it. We're trying to keep this conversation going and encourage the use of this stuff across the space domain. Not just at NASA, but also with our other government members. So again, thanks for being here. And with that, I will hand it off to whoever's next. Thank you. I guess I have some time for questions. If anybody has any questions. Yep.
So what kind of standard, I know we were in the lab and we saw all the different tool points and stuff. And there was that one final one they showed us. That was supposed to be Awesome.
Yeah.
Is that like the standard you're trying to push out then to all of industry? It's also
So I didn't mention Confers, but Confers is a kind of a sister organization to Cosmic. That's an international 501c3, that's working standards. And so it's really important, I think, to understand where we are in the standards is that group is defining functional requirement type standards, performance type standards, but not fit and function, not form and fit type standards. So, but there are specific interface solutions getting built, and we're trying out several of them. And I think we're learning which ones work best. And so I think at some point we do get to a point where we say, this is the form, fit, and form that we want to use. But like in your car, the standard for refueling your car is not overly prescriptive, so how prescriptive do we want to get? We're learning as we go. Counterexample, of course, is USB-C, which we got to after decades of trying other things. So that's kind of the situation we're in now is we need to do it a lot more before we're able to actually pick one that we're going to use all over the place. But I didn't say it, but that FFR also has 3 different power and data interfaces on it. So same kind of thing. We're learning about the different ones. They're all commercially provided. We're learning about them. We're going to see how they work. I would love to see every spacecraft launch with some kind of an augmentation port on it, like a USB port, so we can plug new things in later. But I'm not ready to say that I have a recommendation on which USB solution we would want to use, for example. Other questions? Yeah.
I love to hear that. But my question is, there's enough group of and so people have want to stay. I said,
Okay. Now your water, that's from, okay.
people that. So I love to hear about that. I just found out about the Goddard space systems. That mission, really excited. Is there any other contract that you work with, like the area of ICE?
Yeah, so I guess for the folks online, the question was about, finding employment and with maybe some subcontractors or contractors. And for NASA, I've seen the recommendation that you should go to the NASA center you like and go and on the web page, we all have, lists of contractors that work with us, and that's a good way to learn who they are. I also recommend, Cosmic is a great way to meet those people. Participate in all of the Cosmic focus areas. There's a virtual convergence happening in June that's free for virtual attendance. There's another one with Confers that's happening later in the fall. But that's a good way to learn who all the people are and what they're all doing. There's also something called the ISAM State of Play, which has a list of all of the activities happening in all the different areas. So say you're interested in welding, you go to the State of Play and see the welding.
Can you guys hear me? Sorry,
Yes.
this is the voice from above. I'd love to listen to you for an hour, but we're gonna have to get started with the
We're going to
brief
finish
today.
the question and then we'll go.
Okay, absolutely.
Yeah, because it's 11:15. So we're ready after this one question. So anyway, go look at the State of Play and find who's working on those things and use that as a way to find the companies that you might apply for. Okay, sorry, Jacob, go ahead.
Okay, yeah. So we're ready to get started. Our first team up today is I should have this memorized. Is Oscar at VT. So you guys can come up and don't worry, you'll get your 2 minutes back. Just a reminder that whoever's speaking has to speak into the microphone so we can hear you online. I know in the room you probably don't need to, but yeah, definitely speak directly into the microphone.
Okay. Either or. Okay.
We practiced with the, wait, what? Yeah, we did it here. Yeah, we practiced this. We're just. Yes, please. Thank you. Okay. Yes, sir.
And then one of those.
Okay, you guys, it'll work
Are
out.
we going in order?
Yeah, okay.
Testing. Yeah, it works.
Test.
Yep, go ahead.
Yes. Okay, awesome. I'm gonna go ahead and start right now. Okay, hello, good morning, and welcome to Oscar at VT. We are the Orbital Servicing Capture and Repair Project. And next slide, please. Here's a brief overview of our team organization style. We have team lead, 2 chief engineers, and our team is split up into command, communications, and environments, power, thermal, and propulsion, payload, structures and launch vehicle, and our guidance, navigation, and control team. Next slide, please. Brief overview of what we're going to present. Our impact on the ISM community, specifically servicing, which is our track 3 orbital servicing. Then the big bulk of our presentation is our mission design, so focusing on the analysis and trade studies, and then down selections. And finally, our conclusion with our lessons learned, project management, and our path to PDR. Next slide, please.
So here's our executive summary. The main problem that we identified was that there are a number of long-lived scientific payloads that still had fuel, but their external instruments, such as batteries or transmitters, those kinds of things, were degraded. And we proposed that we could further extend their life by replacing those components and inspecting other components to ensure that future degradation can be ameliorated. So we've completed our conceptual design. We've done a bunch of trade studies, and we are now on the way to PDR. Next slide, please.
So the clients that we selected to demonstrate our capabilities are NOAA 18 for component replacement and Landsats 8 and 9 for inspection. The reason we selected NOAA 18 is because battery degradation and transmitter failure were the primary cause of end of life, meaning that if we can replace those 2 components, the satellite would likely regain most of its functionality. And since it is currently pacified, there is no risk associated with accidental damage to the client. Additionally, there are other missions which have had similar failures, such as NOAA 15 and NOAA 19. Inspection of Landsat 8 and 9 was chosen primarily due to its close proximity to NOAA 18 and their high value of around $1 billion. We believe that these clients are sufficient proof of concept because the capabilities required to replace the external components on NOAA 18 are generally applicable to external components on most other satellites. Systems in a similar cost range to NOAA 18 and Landsats 8 and 9 are ideal for Oscar services because an Oscar mission would be significantly cheaper than a full replacement while still leaving plenty of room for Oscar to profit. We believe that our mission is innovative because autonomous component replacement, rendezvous, and docking are still fairly novel concepts and are at the technological frontier of space systems capabilities. We also believe that our mission is feasible because the external components on NOAA 18 are very accessible and because of technological advancements that have occurred in commercial off-the-shelf space-rated robotic arms, and we will touch more on that later. Most importantly, though, the technology and capabilities required to replace the external components and do close-in inspection autonomously of high-value systems could provide low-cost revival and extension options for hundreds of existing and future missions. Next slide, please.
So this is our Oscar mission concept of operations. We have our mission broken down into 7 main phases, starting with launch and going to our end of mission. If you start in the bottom right corner in our phase 1, you will see our launch and orbit initialization. We will ride share on a Falcon 9 and be dropped off in an SSO orbit. Our launch date is on September 19th, 2029, and we'll launch at 10 a.m. from Vandenberg. The SSO orbit we're dropped into is 495 kilometers, and we will wait 1 week after getting off of our rideshare, and then we'll go into phase 2. Phase 2, we have 2 separate modules of our satellite, which are Obelisk and Asterix, our payload and propulsion module. After 1 week of waiting, we will combine together into one satellite using a Gemini port, as shown in the photos there, and we will communicate with each other using 2 S-band transmitters. And then we'll go into phase 3, our rendezvous with NOAA 18, using a series of RAN inclination and altitude changes. We will rendezvous with NOAA 18 and then move into our 4th phase, docking to NOAA 18. Once we get close to it, we will perform 3 R-bar hops, which help us reduce our risk while approaching, and then go into a natural circumnavigation. And once we complete an inspection while in natural circumnavigation, we will proceed to dock to NOAA 18 using an MIV1 port, as you could see in the photos there. Once docked, we will need to replace their batteries and S-band transmitter. On our satellite, we have a rotating battery drum, as you can see in a photo there, with alternating 8-cell and 9-cell battery replacements and the S-band transmitter in yellow. For our specific phases for replacing the batteries, we will start by using a bolt driver tool to remove the 6 bolts on each battery. And then we will scrape off the adhesive using an adhesive scraper. And then we will pick up the battery using a Naasz style Gecko gripper. And then once we're done with that, we'll use similar methods to replace the S-band transmitter. And then we will continue on into phase 6, which is rendezvousing with Landsat 8 and 9 to perform inspections. And you could see our CAD images with highlighted different systems on the bottom right corner. We have our propulsion equipment in green, our power equipment in red, our comms equipment in yellow, docking in blue, and our robotic arms in white. We will use the GIT AI inchworm arms, and we will have 4 of them. And for some of our key specifications, we have a total mass of 1,046 kilograms and a size of about 1 meter by 1 meter by 2 meters, and plus the length of our arms, which can extend all the way to 2 meters, but we'll be able to move in different orientations as well. We have a power storage of 5 kilowatt hours, and our total mission cost will be around $33 to $36 million.
Next slide, please. So here you can see our block diagram. As mentioned, we have 2 different modules which unified to become our whole spacecraft. So they each come with their own communication system, attitude and orbit control, propulsion, etc. But as you can see, they do have a crosslink of RF prior to docking, and then once docking, we'll be using SpaceWire for the interfaces and power. And then I'd like to also draw your attention specifically to the AI XQR reversal for specifically running our autonomous programs, and the payload bay within the payload module, which will store our servicing equipment. Next slide, please.
We used a trade study to determine the best launch architecture for our mission, looking at 5 criteria for evaluation, the most important of which we determined to be cost and reliability, which we characterized using historical success rates and a Eulerian smoothing factor to account for small data sizes. And from our trade study, we determined the SpaceX rideshare program to be the best fit for our mission, specifically using 2 XL plates for 2 separate modules that will recombine once they reach space. This was largely due to the cost effectiveness of splitting our module in 2 rather than using a program with larger capability to keep it all in one space. And also from this decision, we were able to determine the loading and environment we can expect during launch. Some of the requirements driven from that are shown at the bottom of the slide, most important of which is the max mass that each module can reach, which is about 800 kilograms. Next slide, please. This is Asterix. It serves as one of the 2 primary components of Oscar. It also serves as the propulsion module, and it is able to dock to Obelix via the docking mechanism that is shown in the bottom left corner of the diagram. Asterix is also composed of aluminum 6061, which offers structural support, protection from radiation, and it is easy to manufacture. As mentioned before, Asterix is the propulsion module, so you can see that there's the xenon tank in there, the green propellant tank, and the helium tank as well. In addition to that, Asterix is home to all of the tools used for the battery replacement. The robotic arm is able to easily access these tools via the interface, remove the tools, complete the battery replacement, and then put the tools back into the toolbox. Finally, Asterix is home to some of the most important components for GNC, including the star trackers, the gyroscopes, and the magnetotorquers. Next slide, please. And here you can see a CAD model we did for Obelisk, our payload module. On the left side of the screen, you can see an exterior view of Obelisk with the interface it uses to dock with Asterix on the top, and the client anchor it uses to anchor itself to NOAA 18 on the bottom. You can also see how some of those robotic arms will fit within the rideshare volume provided by SpaceX, as well as some of the arm interfaces that they can use to inch around our module and access different parts of the client. On the top right, you can see an interior view of our module. The majority of that
volume is taken up by our replacement components drum, which is currently outfitted for the NOAA 18 batteries. There's also various GNC, communications, and propulsion components located in there as well. And then on the bottom right, you can see our open deck, which houses the majority of our inspection equipment. Next slide, please.
Now, in order to unify Asterix and Obelix, we're going to be using a Gemini Agena style rigid dock. This is a conical shaped dock with the male side being on Asterix, our chaser, and the female dock being on Obelix, our target. This will provide both load bearing and data and power connections in order to unify Asterix and Obelix into one full spacecraft. Now, in order to actually anchor with our client, we're going to be using an MEV style probe. This is a probe, as you can see with the animation, that is inserted into the client's apogee kick motor. The spreaders expand, giving us full axial loading using the combustion chamber sides. LiDAR allows us to align our probe properly with our nozzle. And heritage for this includes, as mentioned, the MEV1, which means that this is technically a sort of a commercial off-the-shelf, well-tested type of equipment. Next slide, please.
Once we have successfully docked to the client satellite, we will begin component replacement operations. There's two driving requirements, the first of which being the system payload shall be capable of accessing and manipulating mechanical and electrical connections between the client satellite, in this case NOAA 18, and its external components, and that the payload shall be capable of safely storing and transporting the replacement components, the tools used for the replacement, and also the dead components once they are removed from the client. To do this, we'll be using the GI-TIA inchworm robotic arm that was mentioned previously. It's commercial off the shelf, but it is space rated. And the arm, as the name suggests, will be able to extend and retract around the satellite, connecting at different ports around the perimeter of the satellite. And the arm itself has connection points on either end. So we can attach the satellite, disconnect, grab a tool, and then use those tools at any point on the satellite. As far as the tools, we'll be bringing 7 different tools. However, we will be bringing 2 of the gecko grippers for a total of 8 tools. And these tools will be stored on the Asterix module. As far as component replacement for this mission, the NOAA 18 satellite client, we will be using 6 batteries and 1 transmitter that will be stored on a rotating drum on the Obelix module. And then once those parts are replaced, we will store the corresponding parts from NOAA 18 in those same slots. Next slide, please.
To ensure a successful mission, Oscar shall autonomously correct navigation and control errors using sensor feedback. And looking to the left of the slide, we've selected 3 reaction wheels on Obelix, 3 reaction wheels on Asterix, and 3 magnetotorquers on Asterix. These meet the momentum and moment requirements for a safe mission. We also have 2 onboard computers, 1 remote terminal unit, and 2 PCDUs for essential support. Looking to the right, Oscar shall estimate relative position, velocity, and attitude with respect to the client, spacecraft using sensors, and shall be able to maintain an attitude accuracy of 0.1 degrees. To meet this, we have 2 star trackers on Asterix, 4 sun sensors on Asterix, and 5 on Obelix, 2 magnetometers on Asterix and Obelix, and 1 gyroscope on Asterix and Obelix to be able to perform a safe mission. Next slide.
We use SDK to simulate our orbital maneuvers. First, we launch out of Vandenberg Space Force Base, then we complete a 0.9 degree inclination change and coast until our RAN matches NOAA 18. We then burn up to 360 kilometers to match altitude. Then, once we're close in proximity to NOAA 18, we enter 3 R-bar hops to approach it closer, ensuring safe approach. Then we enter natural motion circumnavigation for inspection. And this is here where we go approach slowly along the R-bar to dock with NOAA 18. After NOAA 18, we increase our altitude by 200 kilometers and wait for our RAN to align for Landsat 8, and we do the same for Landsat 9. We do far out inspections for all satellites.
Next slide. For propulsion, we have a minimum delta V, a minimum rendezvous thrust, and a minimum prox ops thrust. We'll be using the BHT 1500 Hall effect thruster using Xenon. For RCS thrusters, we're going to be using Aerojet Rocketdyne GR1 using green fuel. And then we have the respective Xenon tank, green fuel tank, and helium tank for pressurant. For power, we have a power requirement, and then max transient mode, which is our maneuvering. We have a primary battery, a secondary battery,
8.25 square meters of solar arrays. And the reason we have 2 batteries is for asterisks and obelisks to both be independently powered before they can join. Next slide.
Now, with all of the docking going on, there are going to be some major risks. First of all, our inspection risks are 2 main risk vectors. They are our position uncertainty, our ability to realize an impact trajectory before it happens, and then our thruster response time, our ability to change that trajectory in time before impact happens. For that, we used modeling using mainly a Monte Carlo simulation. This gave us at an appropriate risk of 5 sigma. This was determined using a Mahalanobis covariance risk matrix, that if we maintain a radial along and cross-track distance of about 16 meters, we have a minimal chance of impact, and that gives us the most safety. As for docking failures, both for unification with ourselves and with the client, we use Monte Carlo sims to derive our main approach and capture speeds. For our unification with asterisks and obelisks, we found that about 14 centimeters per second gives us a very good capture probability with low risk of impact. And for capture of NOAA 18, our client, we find about 5 centimeters per second to be the most appropriate and safest while still giving us enough time for reactions. Next slide.
For our inspection equipment, we have a quadclops camera to take visual pictures of our satellite during inspection. We have a LiDAR RVS 3000X, mainly used for rendezvous and docking. We also have a DLEM-17 rangefinder as a backup to our LiDAR system. And we have a thermal imaging boson 640 to take IR pictures of our client. Next slide, please.
For our communication systems, we have specifically down selected to use S-band and X-band. We did this because we want to be able to communicate with our clients during inspection or docking of NOAA 18, and they all use S-band architecture, so we'll use that, and X-band for large day loads. Starting with our launch and going to our last inspection, we will be communicating telemetry tracking and command data, as well as position navigation and timing. We'll be communicating with clients and our ground station throughout the entire mission, McMurdo. Our S-band is shown in the ConOps in orange and our X-band in pink. We also have GPS systems on specifically both of our payloads for when we're combining and when we're getting close to NOAA 18 for repair. We'll be using patch antennas for X-band that need a pointing accuracy of plus or minus 3 degrees, as well as 2 hemispherical omnidirectional S-band antennas. Next slide, please.
An overview of our risk summary. I'm going to highlight 3 main risks. Our first being if Oscar enters our client's trajectory, there's a chance that we could collide with them. To mitigate this, as you saw in our SDK simulation, we're going to perform 3 R-bar hops to make sure we have a safe approach. Second, M.5 and M.6, if regarding our docking procedures, slide 17, we were making sure to perform simulations and have an appropriate speed for docking and the correct location. And as you can see on the right-hand side of the screen, we mitigated ourselves from a high-risk mission to a medium-risk mission. As we're still conceptual and entering the PDR phases, we expect to mitigate these risks further as we perform more analysis. Next slide, please.
Now, as for our main mass budgets, we're going to divide them by subsystem. Our structure subsystem has up to 288 kilograms. Our power and thermal has a rather light 85 kilograms. Our dry propulsion is 122 kilograms. This is for both tanks and our plumbing and also our main propellant thrusters. As for our propellants, we're going to have Xenon and our green AFM 315E. Xenon's going to have 91 kilograms allocated, and our green is going to have about 66. Communication has a very light 10. Command and control about 52. That's for both our power distribution and control and our OBCs. Our ADAC system is going to have about 25 kilograms, and our payload has the lion's share of 392 kilograms. Our total mass can go up to 1,046 kilograms, about a ton. Go next, please. Now, this is our power budget, which we divided by power modes. Our main maneuver mode, which is going to be a big bulk. This is when we're changing our orbits. Our proxops, which uses less power, but still quite a lot. Diagnostics, because we're doing circumnavigation, we're mainly going to be coasting and taking photos, much less power. R&R is when our arms are going to be initiated. The arms do have a significant power draw, but still not as much as maneuvering. And then finally, eclipse, when we're out of the sun, we simply cease operations and coast in order to conserve our battery lifetime. Now, this has all been quite a lot, so we actually made a an animation in Blender just to show you how this entire operation is going to go. If you just go to the next slide. So first of all, we're going to detach from our launch vehicle, which is the Falcon 9. We're going to be using their ride share with 2 separate modules. They'll each separate, coast for 7 days. This is Asterix, our main propulsion module. And then we have Obelix, which is our payload module. You can see with its arms. Asterix, the chaser, will approach Obelix. We will make sure that this is our male side Gemini port, female side Gemini port. Asterix will align, get close, use our ADAC system just to get as good as possible a fit. Once we're within range, we approach at about 15 centimeters per second, fully link, get our power and data transfer and our load. This is our client, NOAA 18. We're mainly going to be targeting their batteries, which have worn down by now. These are the batteries, there's 6 of them in total. A transmitter, and we're going to be docking with their Apogee kick motor. This is the MEV style probe, which is inserted into the Apogee kick motor. Our batteries are on a rotating drum. Each of those batteries has a bunch of bolts we need to worry about. They'll go in and go out. In order to actually capture NOAA 18, we will approach from behind. We're going to properly align, insert the probe into their Apogee kick motor nozzle, expand. For the batteries, we're going to first remove their MLI using our cutting tools. Remove the MLI, remove all the bolts. All of them are stored on our drum. Scrape away all the adhesive, remove the battery. Then we're going to add in the new battery.
1 minute warning.
Yeah, and then we're going to reapply our MLI and the bolts. Once that is done, our mission is complete, and you can go on to your next slide.
Thank you. Here's an overview of our program milestones. We can go ahead and go to the next slide. Ultimately, we have developed our AIAA paper and are further developing our path to PDR. Next, Sean.
Yeah, so we've completed our requirement slowdown and general work breakdown system. We still have a couple of major steps left, the integrated master schedule and some stakeholder analysis. Next slide, please.
Lessons learned. We learned that our business case matters as much as our engineering. We learned that from last semester when we focused on a solar shielding satellite, and we pivoted to our repair and replace this time around. Next slide, please. To conclude, you can see our key specifications on the right-hand side of the screen, and we really focused on innovation and feasibility. Feasibility specifically, as you guys saw from our analysis and models, mostly so that we can focus on the 4 identified high-value missions from Cosmic, so that we can be a modular life extension spacecraft capable of inspection, replacement, and repair. Next slide, please. And yeah, questions. Thank you.
So we got 4 minutes for questions, and then we'll do 2 minutes of scoring for the judges, and then we'll get C3PO up. So any questions in the room? So we got one over there, Tammy, as well as a student.
Hi, awesome. Very comprehensive presentation. I'm just very impressed. I think that you may have missed an opportunity to characterize the payload as a modular assembly where you can renew your propulsion with different packages that are client specific, right?
Yes, the dock will indeed allow Asterix to detach from Obelix, and then a new Asterix will come in, take on Obelix, and then Obelix is going to use a storage module to replace and get new components. That is part of the plan. We just didn't have quite enough time to fit into the presentation.
The only other thing that occurs to me, and I'm not an expert in servicing, if you heard me earlier, my background is instruments. There are a lot of components, blankets, wires that it sounds, and material scraped off that it sounds like you're taking off. There has to be a mechanism to capture what's removed, unless I missed that.
Yes, we've been looking into options to figure out what to capture and remove and how that works. Right now, we're very in the early stages, but for our main component thing that we'll hold, we'll have the NASA Gecko Gripper, which it's a new technology that they've already developed and tested, space rated. It doesn't you just stick it on something. It doesn't use adhesive. It uses kind of how geckos stick to walls, and when you're switch mechanically one way. Oh, okay, yeah.
You need something to collect it all in, in the way that what we learned from the tools and servicing. In the drum. When you open your garbage bag or whatever, it was that aspect of it.
Oh,
We got
okay.
a question of how you would capture the pieces that you're taking off.
Oh,
How are you
sorry.
reflecting them all and managing that? No worries.
Yeah, we have a threaded insert board for our bolts, and that's what we've started thinking about, like where to put them when we take them out and place them in. So extra spots and ports on the side for holding any materials while we're removing stuff, so we could place it back in our component drum.
We have another question? Just, we don't have to bring it too close.
Hello. So you said that when your two sections are approaching each other to dock and connect, that they were approaching at 15 centimeters per second. That seems, sorry, was that correct?
That is the maximum speed that is allowable by our aluminum frame and our ADAC response system. This is essentially the very last step when the female and male ports fully insert and lock.
Okay. I thought that was interesting because 15 centimeters a second seems pretty fast. And I was just wondering if you had
It's an upper limit.
an upper limit so that the two docking ports can actually collide at that speed and that would still be able to secure.
Yeah, that's our upper limit. It's basically our do not exceed speed.
Awesome.
All right, now we got 2 minutes for judging. Thanks, guys. Great presentation.
Thank you, guys.
And if the C3PO team could step up to the podium if you're presenting in person. And so just for transparency, what we're doing is 24-minute presentations, 4 minutes Q&A, and then 2 minutes for the judges to score. So C3PO, you're online, I believe. You can take it away whenever you're ready.
Hello, we are Team Cosmic Capstone Challenge, Pad Operations, also known as C3PO from Virginia Tech. Thank you for tuning in for our C3 Lunar Operations Solution Outbrief. Next slide.
Our team seeks to address some of the challenges associated with launching and landing on the lunar surface. During launch or landing, regolith plumes can be ejected by the lander's thrusters, ejecting regolith at high speeds, damaging nearby infrastructure and potentially the lander itself. Our solution is to manufacture a landing pad with interlocking tiles manufactured solely from in-situ resources that are capable of withstanding the weight and thrust plumes of a variety of classes of landers. For this mission specifically, we are proposing a small-scale landing pad using in-situ resources capable of withstanding the loads of the Griffin Lander's attitude control system thruster. Currently, the status of our project is that we have manufactured half-scale tiles with LSP2 simulant via thermal sintering, shown in the bottom corner, and the status of our supporting systems is at a PDR level. Next slide.
Our team consists of 12 aerospace engineering students from Virginia Tech. We are broken up into 6 subteams, with all members being a part of 2 subteams. We additionally have guidance from our faculty advisor, Dr. Kevin Shinpa, and our mentor, Tim McAvoy. Next slide. So in the spring or in the fall, we were able to select a program manager. We defined our mission scope and capabilities, as well as defined system requirements based on the scope and capabilities, as well as the C3 RFP. In winter, we completed a subsystem requirements review. We completed trade studies for our subsystems, and then we were able to complete a finalized conceptual design for our overall system. In the spring, we now established a path to PDR. We're now presenting our C3 outbrief, and we hope to present our PDR in the coming month. Next slide.
For our program timeline, we have it broken into 3 stages. Stage 1, conceptual design and prototyping, with estimated completion in Q4 of 2027. This begins with mission start, where we identify the problem and our preliminary mission requirements, then moves on to CODR, where we refine our system requirements and develop subsystem requirements, PDR, where we develop cost, mass, and power budgets alongside beginning the design of our subsystem, And finally, CDR, where we finalize the design of our subsystem, update cost, mass, and power budgets, and bring in prototyping results. For stage 2, manufacturing and testing, with estimated completion in Q4 of 2029, we have STR, systems testing review, where we have manufactured systems, updated cost, mass, and power budgets, and bring in our systems testing results. Lastly, FMSR, full mission simulation review. We have a fully manufactured and integrated system, finalize cost, mass, and power budgets, and present on our fully integrated results. To wrap up our mission, we have launch and operations with estimated completion in Q1 of 2030. Next slide.
Our system requirements were derived entirely from the C3 RFP. The system shall have a mass less than 200 kilograms and occupy a volume less than 5.58 cubic meters. The system shall survive the lunar night. The system shall interface with the Griffin lander while also communicating with the Griffin lander. The system shall also demonstrate some in situ manufacturing capabilities while also surviving the environmental conditions on the lunar South Pole. Next slide.
Our mission consists of 3 phases and is expected to take 46 flight days. Phase 1 begins on flight day 4 with the deployment of SABRE to the lunar surface. SABRE is our surface prep analysis, building, and excavation rover. And once on the surface, it will search for a sufficient place to deploy deploy Kyber, our kiln for yielding building elements from regolith. Once Kyber has been deployed, SABRE will continue and map the entire 10-meter radius area around the Griffin lunar lander using its LiDAR for a local 3D map. Next slide. Phase 2 begins after the completion of phase 1, is expected to last from flight day 7 to flight day 45 with a 14-day stop during lunar night. We begin by having SABRE flatten the pad site. Once the site has been flattened, it will collect lunar regolith and deliver it to Kyber to be sifted. While SABRE is flattening the site, Kyber will begin its warm-up procedure, going from ambient to 750 degrees Celsius. Once it reaches 750 degrees Celsius, the sifted lunar regolith will be used to fill the mold, and then Kyber will ramp from 750 degrees C to 1200 degrees C and hold for 10 hours. During this 10 hours, the tiles will fully sinter, and upon completion of the 10 hours, we'll ramp from 1200 degrees Celsius to 750 degrees Celsius, then release the tile onto the lunar surface to passively cool. After the tile has been dispensed, SABRE will maneuver over to Kyber, collect the tile with its robotic arm, maneuver back to the pad site, and place the tiles. Each tile placed will be inspected to ensure proper alignment and interlocking using the camera. This whole process will loop from 6A to 9A for the duration of phase 2. Next slide. Phase 3 takes place on flight day 46 and begins with a 20-second firing of the Griffin lunar lander's ACS thruster. SABRE will record the pad using thermal and optical cameras during the test. Once the test is concluded, a post-test inspection will be performed using SABRE's LiDAR and optical cameras to capture a 3D model of the pad and high-resolution up-close images. All of this data will then be downlinked to the ground for further analysis. At this point, our mission is complete. SABRE and Kyber will continue their production and assembly until failure. Next slide.
Our primary mission impact are our lunar landing pads. These lunar landing pads aim to mitigate regolith plumes, which kick up regolith dust that send them flying at almost 2,000 meters a second, which can cause severe damage to nearby infrastructure. These landing pads create known safe landing sites, as well as allow heavy class vehicles to safely and stably land on these platforms. Some alternate use cases are roads and walkways. These roads and walkways reduce the power draw during vehicle travel by increasing traction, as well as reducing the risk of damage to spacesuits. Our interlocking tile design can also be used for structural foundation for permanent lunar infrastructure, as well as radiation shielding with the combination of materials such as aluminum. Next slide.
The surface prep analysis building and excavation rover, also known as SABRE, is shown on the top left. Some notable features are the rocker bogie suspension system, solar panel, the robotic arm, which consists of an optical camera, a claw to grab and place tiles, a scoop to collect regolith and prepare the site, In addition, Sabre will navigate and perform pad inspection through LiDAR, thermal camera, optical camera, sun sensor, IMU, and wheel encoders. The regolith will be delivered to Kyber for tile manufacture.
Kyber is our kiln for yielding building elements from regolith. Kyber will sift and dispense lunar regolith particles that are less than 100 micrometers. It will then flow into our two-piece silicon carbide mold that will then be successfully sintered in our thermal oven. Kyber is capable of manufacturing one tile every 14 hours. Next slide.
Looks like we went back a slide here.
The primary mission innovation is Team C3PO's tile design. Compared to typical designs from the ESA, where tiles are symmetric, they don't completely interlock. Similarly, NASA has created a concept, but it requires two pieces as seen in the bottom left image. Project C3PO has designed a tile that incorporates both of the key aspects from the ESA and NASA. In the top right image under proposed tile design, we have created a tile that has both male and female connectors highlighted in red and green, and they only require a single two-piece mold for creation. The tiles can then be placed in a diamond up and diamond down orientation, which helps create our next launch and landing pad. Next slide. To support advancing high-value missions through NASA's Moon to Mars architecture, we're aiming to create lunar infrastructure in hopes of transportation and future habitation. To progress further from our successful demonstrations, increasing a vehicle size would enable manipulating larger tiles and also allow for faster transport of said tiles and lunar regolith. And scaling up the tile design would also allow for higher thermal and structural loads on the tiles. Largely scaling the mission would ultimately advance sintering techniques. Next slide.
To test our design, Sabre will prepare a 1/4 square meter landing pad onto a prepared area with using 25 tiles of our own design. The test will consist of firing the ACS on the landing pad for 20 seconds. To evaluate the performance of our tiles, we will collect thermal data during the firing and construct a temperature distribution across the tiles before and after the thruster is fired. Using particle shadow velocimetry, we can estimate the velocity of ejected regolith particles to determine the dust capability technique, dust mitigation capabilities of the landing pad. Then, using high-resolution images, the structural properties of the landing pad after the firing can be found and tiles inspected for fractures and deformations. Next slide.
C3PO has successfully demonstrated one of our operating sequences in the form of our tile placement demonstration. In the upper corner, you can see the tile placement demo of our prototype robotic arm picking up and placing our 3D printed tile design. In the bottom corner, you can see the required placement order for our tiles. First, we must place all the diamond up tiles, then place all the diamond down tiles in order to lock the pad together. To the side, you can see a rendering of placing our tiles on the moon using Sabre's robotic arm. Next slide.
This is our ConOps for communication and data handling. We begin with the launch on the Falcon Heavy from Earth to the moon. During this time, we're sending a 10 beat per minute heartbeat via RS-422 from Sabre to the GLL. We then semi-autonomously deploy the GLL and GNC initialization begins. At this point in time, we also start lockstep computation. The GLL communicates directly with Earth via X-band RF, while Sabre communicates directly with the GLL through Wi-Fi, and Kyber communicates directly with the GLL through wired RS-42 connection. The GLL sends an initialization message to the ground, and then Sabre checks for an obstruction under the GLL ACS. If an obstruction is present, we move on to the opposite thruster. Sabre then sends the testing results back to the GLL, and the GLL sends the testing results back to ground, again through X-band RF. The final payload status is transmitted back to Earth along with all test data from our experiment. Next slide.
To design the mobility system of the rover, we took into account the lunar terrain conditions and the operational radius of 10 meters around the lunar lander. We selected a rocker bogie suspension, given that it allows us to distribute the weight evenly among the wheels, and it also maximizes contact area with the terrain. In addition to that, the aluminum and chassis are made, the chassis and the suspension are made out of aluminum with a coating made out of chromium carbide nickel chrome that helps with it helps to prevent the abrasion caused by the lunar dust. We have flexible wheels that maximize contact area with the terrain, and they are made out of steel. Next.
This is our trade study table of different tile assembly methods. We researched 5 different tile assembly methods, including thermal oven, microwave sintering, geopolymerization, laser sintering, and flash sintering. Each of these methods was weighted against 4 different criteria, including power, mass, time, and cost. Of these 5 methods, there were 2 methods that clearly stood out above the rest, being a thermal oven and microwave sintering, with thermal oven ending up winning due to its low power requirement to successfully sinter, as well as its low mass cost. Microwave sintering had a very low sintering time, but the power requirement to successfully sinter one of these tiles was way too great and a lot more than we were capable of. Next slide.
Sabre and Kuiper must be able to operate on the lunar South Pole, which experiences temperatures that range far outside of what several of their critical components can safely operate in. To address this, we've designed a thermal control architecture centered around a highly insulative warm electronics box, or web, which is coupled with a 1.1 square meter radiator that rejects any excess heat from the web during lunar day. We've also added a Capstone film heater, which can provide up to 10 watts of continuous heat during lunar night. An MLI is wrapped around all temperature-sensitive components for insulation. Our initial transient thermal calculations on the right indicate that our architecture can keep the temperature-sensitive components on Sabre within the required operational band for a full lunar day-night cycle, with the heater running at just 3 watts during lunar night. Next slide, please.
To support the power demands of our system, we utilize 2 independent power generation systems. Since Kuiper is tethered to the lander, it will utilize the power bus provided by Astrobotic in one of 2 modes, nominal or peak. Nominal mode is used to sustain temperature during the sintering process, and due to higher power demands for ramp up, we will utilize power or peak power mode during those times. For Sabre, we use a combination of solar cells and LiPo batteries to supply up to 560 watts to all systems on Sabre. Shown in the middle is a design of our collapsible solar array consisting of 240 solar cells. During lunar night, our system will interface with the Griffin lander's wireless charging interface to supply 10 watts of power to our thermal control system. Next slide. Assuming that the secondary C3 experiment occupies the full footprint of the payload area, our experiment fits well within the payload volume, coming in at 3.2 cubic meters. We've also estimated a total system mass of 175.8 kilograms and a conservative cost estimate for all hardware at $33.75 million. Next slide.
We've identified 8 key risks to the C3PO system during mission operation, 6 of them being for Sabre and 2 of them being for Kuiper. Highlighting some of the most consequential risks, we have Kuiper mold degradation, which we mitigate using a silicon carbide mold for increased thermal conductivity and mold lifespan. To mitigate Kuiper's damages to Kuiper's sifting mechanism, we utilize 3 sifting layers to regulate regolith particle size. To mitigate Sabre's traction issues, we utilize a rocker bogie suspension system that evenly distributes the weight among its 6 wheels and flexible metal wheels that increase contact area with the lunar surface whenever a load is applied. Next slide.
Throughout the development of our system, we created a prototype tile using LSP2 lunar regolith simulant. To manufacture this, we used a thermal oven at 1200 degrees Celsius for 6 hours inside of a prototype graphite mold. On all interlocking features, we achieved a plus or minus 1 millimeter tolerance. To test this tile, we used the ASTM C39 concrete compression standard alongside a 12.5 millimeter diameter by 25 millimeter long test coupon. We achieved a max stress of 2.44 megapascals. Secondly, we conducted a 2000 degree propane torch burn, where for 2 minutes, we held the torch at 2 inches from a diamond up tile and achieved a max diamond up temperature of 650 degrees Celsius and max diamond down temperature of 70 degrees Celsius. This test can be seen in the video on the right. Next slide.
For our project, we considered 3 innovative concepts. The first concept was a single tile design, which uses this one tile mold which simplifies the manufacturing process and limits the amount of equipment needed for manufacturing. Our second concept is using solar mirrors to focus solar energy on lunar regolith to center it. This is attractive due to its low power requirement. However, due to other mission constraints, such as mass, this was not a feasible centering method. Our last concept was using a GeoL ACS thruster on our landing pad to test its capabilities of our tile design on the moon. This creates a more realistic scenario and requires no extra equipment from Earth. Next slide.
We identified 3 NASA technology gaps that would aid our system if they were closed. Lunar dust tolerant systems. The lunar dust is highly abrasive and electrostatically adhesive, which reduces the mobility of rovers and limits the actuations from actuators. Secondly, lunar regolith excavation. Current terrestrial methods have shown that this can be done with systems less than 10 kilograms. However, full-scale missions would increase ISRU capabilities, expediting the NASA's Moon to Mars architecture. Third, in situ resource identification. This is necessary for centering, as a known particle size is needed for proper material properties while centering. Next slide.
Seen here are 3 of our biggest encountered challenges. One of them was tile design. Designing the landing pad proved to be very difficult. On the right, you can see iteration 1 of our tile design, which was not interlocking and moved very easily. We then moved on to iteration 2 before finally arriving at iteration 3, which was an interlocking tile design using one 2-part mold with holes added for ease of placement with a robotic arm. Mass budget was also a large concern. We only had 200 kilograms provided, so we had to scale our landing pad and tiles accordingly. Lunar night survivability was also an issue for us. We only had 10 watts of power from the GLL and limited heating capabilities. So to address this issue, we developed a web to protect our temperature-sensitive components. Next slide.
Our paper details the analysis behind the options and the decisions we've made with the system. It contains an abstract of 142 words. It is a total of 20 pages and references 49 other papers. We hope to submit our paper to one of AIAA SciTech, AIAA Ascend, or IEEE. Next slide. To summarize, the problem being addressed is the high risk of lunar regolith and dust affecting future moon missions. Lunar dust may be launched at dangerous speeds during landings or launches, causing harm to nearby infrastructure or people. C3PO's solution is to autonomously manufacture and construct a landing pad through in situ resource utilization. This has led to the development of our Kyber and Saber systems. Kyber and Saber aim to work together to autonomously excavate regolith and prepare a plane for placing the tiles, delivering sintered structural tiles to the pad and assembling them in an interlocked fashion. To verify our results of our test mission, we would then request the Griffin lunar lander to fire its ACS thrusters directly onto our test pad. After that, we can use Saber's onboard camera systems to analyze any deformations, damages, or displacements of tiles after the test firing. With this test, we hope to achieve significant reduction of dust plumes caused by landing on the moon and support future missions to and from the moon, such as for Moon to Mars architecture. Next slide. This concludes C3PO's final outbrief. We now open the floor to any questions.
All right, so we got a little more time for questions. Let's see if we get any in the room first, and then we can get to online.
Hi, guys. So I like the concept. I saw that you're doing optical inspection of the tiles. Did you consider strength testing of the fabricated tile or the interconnection of the 2 tiles? I think that's probably important for the, longevity of this concept.
So we did consider doing strength testing. The main prohibiting factor is just the amount of mass required to do proper testing. It's just the most deflectometers are just too heavy to fit within our payload budget. We also felt that the majority of this testing could be sufficiently done on Earth prior to launch.
Any other questions in the room?
Questions in the room?
Andy Quas has his hand up.
Oh, great. Andy, go ahead.
Thanks. Great job, guys. I tracked it as best I could in such a short period of time. But a couple quick things. How did you address the unknowns associated with the environments that are somewhat defined but changing on the lunar surface all the time? You know, whether or not it's in sun or not. You know, whether you're getting any movement of the regolith while you're trying to, you know, take care of adjusting it. So can you talk about that a little bit? And also, does the system lend itself well to being able to verify what you ended up with after you did what you think you did? In other words, what's the verification plan to assure that it's where it's supposed to be?
To address the lunar South Pole environment, which you're correct, it's very unpredictable, very extreme, not friendly to spacecraft. We did a lot of research on the lunar day-night cycle to figure out what kind of temperatures our rover and oven would experience throughout the whole cycle, and modeled our transient thermal simulations accordingly. We've also, it wasn't mentioned in the presentation, but we've designed all of our components to be dust resistant and radiation resistant to prevent any sort of damages happening there. And we travel at a very slow speed to mitigate any sort of dust kick-up from the wheels or anything like that. Just furthermore trying to prevent any sort of damage that might happen there.
For confirmation and just like to deal with slippage in general, we're using SLAM, which allows us to use local landmarks that we've modeled or that we've scanned with our LiDAR. And that allows us to know where we are. Even if we slip, we have closed loop feedback on that. And then also for the tile inspection, we're using both LiDAR and optical techniques in order to look at how exactly they're placed and confirm that they're interlocked. So we're able to confirm that after the fact.
Any other questions? We got 5 minutes.
Hi, Bo Naasz, great work. So my question is, do you require the Griffin lander to survive the night, or can you get the tile built under its thruster before nightfall?
Yeah, the Griffin lunar lander supposedly is supposed to survive lunar night. That's what that other 400 kilograms is said to be used for. Now, theoretically, we can produce 25 tiles in less than 14 days, but the additional setup procedures require a couple days on their own. So we would not be able to manufacture all 25 tiles before lunar night.
Okay.
Anything else? We got 4 minutes until the next presentation. Oh, we got one in the back.
Thank you. You guys did a lot of different iterations and testing. What was the most surprising thing you learned, and how did it lead to new innovative ideas?
Probably the most surprising one was how much of a change the sintering time makes on the strength. So initially, we were going based off of a few research papers we had seen, and we got sintering strengths that were well below what we were expecting, with only a 20 minutes to an hour worth of sintering. So then we increased to 6 hours, and this massively increased our strength. I think it was something like 4 times stronger. And then that was with our 6 hour sintering. Then we recently, just a couple days ago, we tested our test samples at 10 hours. And these were able to support over 1 kilonewton on a teeny tiny little cylinder. So this was a massive improvement, which is why we chose 10 hours for our entry time.
Any other questions in the room or online?
Andy Quast, did you have your
Yeah.
hand up again?
Yeah, if you got time, I'm going to use it. So, can you tell me a little more about Kyber? I might have missed it, but is it a standalone or is it intended to be in a controlled habitat or some kind of environment? And if it is, what's the process for placing and removing as they become fully complete?
Yeah, so Kyber is a standalone. It's connected to the lunar lander. The way that I'm assuming you're asking about the tiles once they're dispensed. Is that what you are asking about, or are you asking about the placement of Kyber itself?
No, piles, individual.
Yeah, so once the tile was successfully sintered and cooled down to the desired temperature that we have researched at, which is 750 degrees Celsius, the two-piece mold separates and allows the tile to fall down through the dispension system, and then Saber itself will use the robotic arm to pick it up and carry it to the desired location.
So Kyber sits directly on the lunar surface and does not require any external environmental control. And all of the cooling after 750 degrees C happens passively with the tiles sitting only on the lunar surface. No additional environment required.
All right, thank you. We'll move on to the next presentation. Thanks, C3PO.
Thank you so much.
Thank you.
Next up, we got H2 Space from University of Pittsburgh.
Okay, guys, just make note that this clock is 2 minutes behind.
Yeah,
So
clock in the back is 2 minutes behind. I have a stopwatch here that I'm watching, so I'm kind of looking at that. And you can go ahead.
Hey, Alec, we don't have audio right now.
Okay, we're working on it. Can you hear me right now?
I can hear you right now.
Okay, so it's just a mic issue at the front. Pausing the timer.
okay.
So battery life on the mics is pretty bad here.
Okay.
Okay, starting over.
All right, hello. We are H2 Space from the University of Pittsburgh. We are presenting today the Ground Regolith Unit, also known as GRU. Next slide, please.
Hi everyone, my name is Anthony. I'm a material science engineer.
I'm Joe, I'm a mechanical engineer.
I'm Lucas, I'm also a mechanical engineer.
I'm Nathan, I'm a mechanical engineer.
I'm Steven, I'm a computer engineer.
And I'm Zach, I'm also a mechanical engineer. Next slide, please.
So the purpose of our mission is to start creating lunar infrastructure. Right now, there is no current way to have any type of livable way to conduct research or future experiments. So what we are presenting is GRU. It is not currently energy or cost effective to transport material, any type of building material from Earth to the moon. So the idea is to utilize the moon's resources, which is regolith, which is all the dust that surrounds the moon. GRU is a regolith excavator that collects lunar regolith, and this will lead to different types of building materials that we will create. And this ultimately decreases the total energy needed to transport materials to the moon and create this, and then also decreases the total mass and costs. GRU is currently in its testing stages for key concepts such as its suspension system, which will raise and lower its chassis, and its excavation system.
Next slide, please. So as Joe mentioned, the ground regolith unit will be responsible for collecting lunar regolith, but where does that fit into the higher value missions? It will serve as the first step of collecting the lunar regolith, which will then be later refined and turned into bricks and other building materials for lunar infrastructure, which will be key in creating lunar outposts on the moon, which will not only serve lunar missions, but also as a launch point for further deep space missions in the future. Next slide, please.
Here's just a brief outline of our progress throughout the year. In the fall, we kind of identified our operations, which are gathering and transporting lunar regolith. And then in the spring, we conducted trade studies on our main systems, finalized our conceptual design, and this month we developed our path to PDR. Next slide.
So the general outline for what the mission of GRU will look like begins with the launch and the landing on the lunar surface on the Griffin lander. After, we'll deploy the ground regolith unit to get some initial communications to see and make sure all system functionalities work. After that, we'll begin the life stage of the rover, in which regolith will be collected at various sites and deposited at selected locations based off of mission plans. After that, the unit will return to the Griffin lander to recharge, and it will repeat this process throughout its life. At some point, we expect it to possibly need maintenance, in which astronauts who are on the moon will be able to work with it to update it and develop it further. And then eventually we expect an end of life. Next slide, please.
So the ground regolith unit will consist of two main operating systems. The first is the actuating suspension, which is a modified version of the rocker bogie system seen on other rovers. This suspension consists of two sections on each side of the rover, which will use servo actuated joints to raise and lower the chassis. And the digging head is mounted to the frame, which will be raised and lowered solely by the actuating suspension. Additionally, the front and back tires of the unit will have the ability to rotate to enable the unit to turn on the spot. Next slide. Once the regolith has been picked up by the digging head, it will be deposited onto a conveyor belt system within the unit itself. First, it will go on the primary conveyor belt, which will then take it onto the secondary conveyor belt, which it will remain until it is time to unload. At that point, a hatch in the back will open and it will be deposited off of the unit. Next slide.
We conducted a trade study for the materials we were going to use for our conveyor system. Initially, we sort of thought of using a linked structural material, but due to weight constraints, we decided we would have a film or fabric kind of wrapped in tension over our conveyor roller bars. Our main concerns were the service temperature, the film being possibly prone to fracture and puncturing, the tensile strength of the film chosen, and triboelectric charging. Ultimately, we were between Teflon and Captain films, and we decided Teflon would be a better choice as it can be reinforced with glass fabrics to increase its fracture toughness. And our main concern, though, with using Teflon is that triboelectric charging. The lunar regolith is electrostatically charged, so there were concerns about it sticking to the fabric and potentially jamming up our system over time.
Next slide, please. So we made 3 different iterations of our digging design. We were planning to print the wheels separately and then test them using sand substitute as regolith. So the most important thing we weighted was the volume extracted, then the volume retained, and the least important was the mass of the wheel, as they all kind of took a similar amount of material. We ultimately went with the bucket wheel design as it was very efficient compared to the 3-spoke design, and the 4-spoke design could serve as a future option given more test. Next slide.
So we also conducted a trade study for the material we would use for the digging head. We looked at carbon fibers, aluminum alloys, as well as titanium alloys. Quickly, we ruled out carbon fiber just because there was concern about delamination just from the jagged regolith dust that we're picking up. Ultimately, we decided to go with titanium because of its greater abrasion resistance. And in future designs with our digging head, we hope to incorporate carbon fiber maybe for some of the structural aspects of the digging head just to reduce that weight.
Next slide, please. So after this, we did a trade study on different tire designs. We looked at the Bridgestone second generation lunar tire, the spring tire, and a traditional tire seen on rovers such as the Curiosity rover. One of the main concerns we had was durability with the differentiating weights from the lunar being loaded up and then eventually deposited. What we found best was the Bridgestone tire, as it had built-in systems to deal with that different masses. The spring tire had concerns about not only the changing masses, but also the rough surface that we could encounter while digging. So that made it a second good option. However, it was still a little bit concerning. Finally, a traditional tire seen on rovers was overall just not a great option from our studies, as the rigidness of the tire would be a concern with the differentiating masses. Next slide, please.
So to test our designs, we developed prototypes for two of the main systems. The first being the actuating suspension, which you can see in the top two images in both the lower and raised positions. And the second system being the digging head in the bottom two images, for which we used sand as a regolith substitute. Both prototypes demonstrated that our concepts were valid, and we continued on to further testing. Next slide, please.
For the suspension, as mentioned previously, they are utilizing two different servo motors to lift and lower the chassis. The first servo motor at the top being the one that pulls the passive back wheels forward, and that allows us to begin our raising action. And then the second servo motor is attached to the driving wheel, and the driving wheel is meant to be parallel or perpendicular to the lunar surface at all times. That way to give us our raise, and then there will be a third servo motor attached to the driving wheel to do that rotational element so that we can steer our rover. This suspension will be made out of 7075 aluminum, which has a pretty low density and a very high tensile strength. And overall, each of these suspension elements will carry about 800 newtons. Next slide, please. To model this, I did a simple truss analysis utilizing a hollow cylinder cross-section, and with a lunar gravity of 1.62 meters per second squared, the largest sigma 1 was found to be 29.6 megapascals, and the minimum moment needed to lift the chassis with minimum torque is 86.7 newton meters about point W. Next slide, please. And then this is our von Mises stress analysis that of all the different points that we decided to measure of maximum moment and forces. Next slide, please.
So here are videos of our physical testing of our wheel design. We 3D printed them and then slotted them onto a bar with offsets as to avoid dynamic loading. As you can see, the first video was our 4-spoke design. The second one was our 3-spoke design. And our last one you see here is our bucket wheel design. Initial estimates of our bucket wheel design had it at 0.3 cubic centimeters per rotation, although these physical testing showed that it excavated more than what was calculated. More research could be done on new digging designs in upcoming weeks.
Next slide, please. So for the tire design, going off of the Bridgestone lunar tire second generation, we designed a model that would be similar to what we expect for our rover. As seen in the zoomed in image, one of the main focuses was the spoke design, as they were seen as a way to distribute the masses of the rover. We focused on the curvature of the spoke, which helped with the yield stress and breaking up any force concentrations. The outer shell of the tire will be made up of a titanium alloy, while the spokes in the inner hub will be made out of aluminum 7075. We also did a FEA analysis on ANSYS to kind of simulate 2 times the expected lunar mass of the regolith loaded, as well as a torque from the motor to drive the tire. And we found that the tires passed all of our concerns and should, in theory, work. And we are happy with the results that we found with the FEA analysis. Next slide, please.
So for our data handling and communications, we will be using downlinks of TTC, which is telemetry, tracking, and command. Telemetry will be in charge of keeping status of the health of the rover in terms of battery, any damages that are on the electrical side of it. Tracking will be tracking the rover on the lunar surface and giving any future coordinates of where it may go. And command will be the main system talking point of the lunar surface and then the Earth on the ground. We will be using CNDH for the main computer system between the lunar surface and the Earth, and this will be the main system for communications. We'll be using low gain and high gain antennas. Low gain will be at 1 to 10 kilobytes per second. High gain will be about 10 to 50 kilobytes per second. The high gain will be in charge of taking pictures and sending any images from the lunar surface down to the Earth, and the low gain will be for simple communications. We will also be utilizing the map system, which will keep the rover autonomous, allowing for our rover to communicate with the MAPS Cube SAT, which is a satellite already in orbit. Next slide, please. 3 main risks that we discovered were battery life depletion to 0. We decided that solar panels will be used to recharge and capture any energy for the rover. With the solar panels, we will get about 15.5 hours of usage until the battery is completely dead. Rover is unable to move. There could be different holes, and while we're digging, it could get stuck in some areas. So the suspension system will allow for the rover to have some agility by moving it up and down, left or right. And communication failure. Rover is unable to talk to Earth, and we're unable to see where it is on the lunar surface. So there will be a relay satellite that will be the main satellite as backup. Next slide, please. And some additional risks, particle blockage in the system, motor failure, code failure, and electric degradation. Next slide.
So some of the biggest challenges encountered by our design team was the weight, the suspension system, and the power needed for all of the systems. To solve with the weight, we really had to work as a team to minimize the masses and overall weight through each system. We also worked on finding new methods for motors. We were able to find a motor currently in early phases of development that could provide high torques needed at a low mass. For the suspension system that could work with the changing weight distributions, we were able to, as a team, in Joe's idea of having the raising and lowering allowed us to incorporate the rocker bogie system while also accounting for the mass changes of the rover in general. And finally, with the power for all systems being able to work during the rover's operation, the satellite helps greatly with that. As Stephen previously mentioned, the 15.5 hours was found after applying as a solar panel to the top of the rover. So our concerns of having low powers between charging was not a concern anymore. Next slide, please.
So our most innovative concepts considered, we consider tilting a tilting system for the chassis. So we would actuate the front and back suspension to either dig forward or tilt it up to move the regolith. Another one is onboard sintering and refining. So we thought about filtering it on the rover and making the bricks sintering, but our power and weight concerns, we did not continue with that. And another thing we considered is vibration filtering and magnetic sifting. So we could extract useful alloys such as titanium or iron. Next slide.
So during the design of our rover, we encountered many technology gaps. The first and most prominent was the electrostatic charging of the lunar dust that kind of tends to stick to a lot of components. So we looked into some protective material coatings such as ceramic coatings or conductive polyamide coatings. The idea is that we would incorporate these in our most critical systems just to keep the rover protected and extend its life. Additionally, we focus just on the gathering of regolith, so other supporting systems for filtering of regolith, potentially freeze casting or sintering. Shout out the last group, C3PO. Those all need to be developed further. We kind of need all of those systems before the gathering of the regolith is actually a useful endeavor. And also we found compact joint drive systems which are being developed. The idea here is that it uses a two-stage system for its motors and actuators as opposed to a typical harmonic drive which uses 3 to 6 stages. And the main benefit of this is it reduces the amount of components and risk of failure, and then also potentially reduces the weight of all of our motors and actuators, and that weight can then be allocated towards other systems on board.
Next slide, please. So our weight breakdown of the rover, our digging head was one of our main concerns coming into the design. However, we found it to be only the second most consuming of our weight distribution, while the frame of the rover itself was found to be the most. Further developments, we believe, will reduce the weight of the frame, which in return will allow us to focus more on possibly extending the battery life by adding more batteries or adding more cameras and sensors to the rover. Another main concern of weight was the motors. However, with the system Anthony just mentioned on the previous slide, we are pretty confident that this idea of having a lot of weight distributed towards our motors is no longer a concern. Next slide, please. Our path to PDR and beyond starts at phase 2. For phase 2, we'll begin fabrication of further prototypes, allowing for advanced testing. We'll finalize methods for heat generation and dissipation, and we'll do a full FMEA analysis, allowing us to dig deeper into areas that we previously mentioned, as well as those that we did not have the time to focus on. Finally, for phase 2, we'll begin coding the system for the final rover. In phase 3, we'll finalize wheel and suspension design, select final motors, and begin testing. After that, we'll select 2 final prototypes to be weighed for the digging system, in which a final design will be chosen. The conveyor belt system will be finalized and parts will be ordered for construction, as well as the final developed cost expectation for the mission. Phase 4 focuses on finalization of any features that has not previously been mentioned. We'll confirm code functions to make sure that we meet specifications. We'll select final electrical components such as cameras, motors that haven't been already, as well as any sensors needed aboard, and we'll begin the assembly of the rover. Phase 5 will see our final construction of the prototype, vibration testing to confirm that the construction meets all expectations, and if there are any failure points, we'll go back to previous steps and reanalyze them. We'll finish the code and confirm any functionality. We'll confirm backup systems, as well as the final integration of the stereo mapping system for the lunar environment. Next slide, please.
3-minute warning.
So our paper gives more detail about our rover in full. We will keep updating it with any innovative concepts that we decide to apply to it, and we will prepare it for AIAA publication or any other SciTech forums. Next slide, please.
In summary, we identified one of the main problems of creating lunar infrastructure on the moon is the cost of transporting material from Earth. And our solution to that is by utilizing material found on the moon by construction of bricks and other building materials from lunar regolith. And the first step in that is the collection of the lunar regolith, which is what we focused on. And our key developments in this were developing the digging head and the actuating suspension of our rover. Some of our biggest challenges we encountered were ensuring that we would have enough energy capacity through the batteries on board to provide power to all the systems, as well as minimizing our weight to be under the 200 kilogram weight limit. And looking forward in next steps, we will continue development as outlined in our PDR. Next slide, please. And with that, that concludes our presentation. Thank you for listening, and we'll open it up to any questions.
Another question in the room?
There were some questions in the chat. Alec, if you want to, when there's a gap.
Okay. Good presentation. This thing all hinges on the rotating drill design and getting material on the conveyor belt, and the conveyor belt. I see that you did the sand approach, thinking about path to PDR. How are you guys going to convince yourselves? What would be the plan for a flight-like environment with vacuum and electrostatic and temperature gradients, gravity change, et cetera, et cetera? How are you going to, what would be the concept to convince yourself you're not going to jam, the stuff's not going to stick to your drill bit? Thanks.
So we previously looked at testing with lunar regolith stimulants found by different manufacturers. However, unfortunately, that was not in the budget for our project. So our future plan would be to use these similar stimulants to test, the concerns of jamming, electrostaticity, and other concerns. We would also try and focus on testing in vacuum-like environments as one of the main concerns that we could see between the digging head and the conveyor belt system is making sure that it properly lands on the conveyor belt and is able to be brought throughout it. So these concepts would have to be tested in more advanced environments than we had for this project.
Gravity?
Yeah, gravity concerns would be further calculations that we would consider, as is hard to do on Earth. However, we are confident that with the right calculations that our design is able to fit the any concerns that gravity may have in either the digging of the regolith or the movement of the regolith further into the rover.
Got another question in the back of the room, but we have one online, which I think may have been answered already, but I'll repeat it. What material is being used? It looks like there's no dust being lifted. Follow on, how does the tire perform on rocky surfaces, rock/regolith mix?
I'm going to assume that the material being used is for the tire. The tire was the core and the spokes of aluminum 7075, while the outer shell of the tire was a titanium alloy. The tire we decided to design after performs well on rocky surfaces, as the gaps between each set of contact points between the tire profile itself and the surface allows for different movements across the rocky surfaces and makes it so that any bumps that may be considered a little large for our rover are able to kind of be put up onto the medium plate of the tire. If you I wish I had an image up here from a previous slide, but we can kind of use the tire gaps to create leverage to raise the rover itself.
Hi, so I was wondering if you had looked into specifically the long-term abrasive durability of the secondary belt, because it seems like it is constantly being dragged underneath the regolith that you're storing, if I understood that correctly.
Yeah, so that was a big concern, was the abrasion. The idea is that main conveyor and that in the body will kind of only shift the regolith back when need be. So we're not kind of constantly rubbing against that regolith dust. That's just to greatly extend the life.
Hey guys, great work from such a small team. I wonder did you set yourself any goals or requirements for, how much regolith, how quickly, how much land do you have to cover to get all that? How much can you hold in a load? Those kind of things.
So our initial really rough estimate, we have a volume capacity of 0.3 cubic meters, and the rate which our digging head digs at is about 30 cubic centimeters per rotation. So based on our operating time, it would take about 1 hour to fully fill up the rover, and then it can be deposited somewhere else. So we just repeat that 1 to 2 hour process over and over until the end of the mission.
Do we have any other questions in the room? Or are there any online, Alec? If you scroll down.
Online.
Okay.
Oh, wait. So now we'll break for lunch. We'll return at 2 p.m. Eastern. And Colleen wants to grab a picture of the in-person people. And we'll see you at 2. We will instruct you on where to go.
So
You're all in class.
you guys can either
All right, I'm going to start the 30-minute timer now.
All right. Welcome to the MISO, or Michigan In-Space Servicing Orbiter final presentation. Let's get started. So today we'll briefly discuss our overall concept and then discuss our project at a high level and explain the economic feasibility of this mission before diving into details about the operating sequence, system design, and our engineering development work. Lastly, we'll briefly outline a path forward if this work were to continue, and then discuss some of our lessons learned throughout these past 2 semesters. So on the next slide is our executive summary. So currently, the spacecraft paradigm is that we treat satellites as disposable, even when most of their systems still work. Lifetimes are often limited due to fuel depletion or component degradation, leading to costly and inefficient replacements. So we propose an orbital depot that is capable of refueling and robotic component replacement at scale for servicers, and this will act as a central hub for other servicer spacecraft, ultimately laying the foundation for a future in-space logistics network. On the next slide, moving into our program overview. On the next slide, you'll see our team. So we are a team of 5 grad students and 4 undergrad students from the University of Michigan competing in the Cosmic Capstone Challenge with our faculty advisor, Professor Aaron Johnson, and our industry mentor, Dr. Ed Tate. Here you can see our team roles. And on the next slide, I'll outline the process we went through these past 2 semesters. So we started with team formulation in September, where we assigned roles and kind of selected our initial operations and capabilities, and then our system requirements review, which actually led to a major rescope. We completely changed what we were doing. This led to us not finalizing our operations and capabilities until December, and then our system requirements actually being finalized in January. From here, we conducted trade studies across key subsystems and led to our finalized conceptualized design in March. And to support this, we conducted some thermal and radiation analyses. And then from here, we identified next steps for a path to preliminary design review by identifying our key risks and next steps for further validation and refinement. So on the next slide, Our mission focuses on these two core capabilities: on-orbit propellant refueling and transfer, and on-orbit component storage and robotic delivery. So we directly advance these following cosmic objectives, specifically by demonstrating new technologies for ISAM in orbit and facilitating growth of a new on-orbit servicing market. On the next slide, we have our concept of operations. So here you can see our plan would be to launch this depot aboard a Falcon Heavy to effectively a geostationary transfer orbit. From here, we would deploy our satellite and then utilize electric propulsion to circularize our orbit to near geo. Now, one thing I want to make clear here is that our depot aims to be a central hub for other servicer spacecraft. We will need our clients to be independently capable of rendezvous and docking, and equipped with one of our standardized docking interfaces. The idea is that our clients will come to us, obtain what they need, and then depart from us to GEO, where they can service high-value GEO assets. We anticipate the future of ISAM to have many players in the servicing market, and by centralizing critical supplies in orbit, we reduce reliance on repeated launches and enable a more efficient and scalable servicing market. We also plan to rely on resupply missions to top off our supply of sellable propellant and components. After resupply, these spacecraft will transition to a graveyard orbit, and once our depot reaches its end of life, it will also transition to graveyard. On the next slide, we zoom into our actual client servicing operations. So here you can see how we envision carrying this out. Our clients will approach the depot and then dock to one of our 6 interfaces, which are capable of refueling hydrazine propellant directly through that docking interface. Once docked, if they need, we can open our cargo bay doors, grab the requested component with our robotic arm, and then place that component into the client's designated location, wherever that may be. The client could then take that component and fuel and then go to service a high-value asset, which would likely be in GEO. And on the next slide, we can show that we kind of analyzed a business case to show that a depot of this type would actually be realistic. So we initially estimate a launch cost and development of $1.1 billion, primarily driven by manufacturing, launch, and a first-of-its-kind system contingency. When we add in operations, which would be another $550 million, this brings our total lifecycle cost to about $1.65 billion. On the revenue side, we use a tiered membership model combined with annual subscription fees. So Tier 1 would be $50 million per year, and Tier 2 would be $25 million. So in return, customers would get priority docking and discounted rates. We also generate revenue through the sale of high-value components, which are solar arrays, batteries, and antenna modules, as well as storage services. From a customer standpoint, if they come to us for more than 500 kilograms of hydrazine per year, they would fully recover the cost of the membership through the propellant savings alone. Our initial launch cargo would be 7,000 kilograms of hydrazine and then 3 sellable components, which is enough to demonstrate these capabilities and kickstart our revenue generation without having to rely on resupply launches. So on the next slide, you can see our financial trajectory. We would have a high upfront investment phase, followed by about 3 years for our depot to actually reach its operational orbit after launch. After about 4 years of operations, we would break even, and then from that point onward, we would experience strong cash flow as the on-orbit servicing market continues to grow. Moving on now to our operating sequence.
Next slide. So here we can see our launch and orbit insertion plans. So the depot will be launched by Falcon Heavy into an elliptical transfer orbit. This is similar to GTO, but with a slightly lower apogee at about 1,000 kilometers below GEO, which is our depot's target altitude. The depot will then use electric propulsion to circularize this orbit. This transit will take roughly 3 years, which is long but necessary due to the high mass of our system. The next slide shows the sequence of client maneuvers. So the client will first wait for proper alignment with the depot before starting its first Hohmann transfer to reach our depot's orbit. It'll then use a series of phasing orbits to gradually and safely approach our depot before docking to receive all the fuel and components that it needs. Once it stays docked for as long as it needs to, it'll perform its second Hohmann transfer to go back out into GEO. And this sequence of maneuvers assumes that the client starts and ends in geo and is using chemical propulsion to maneuver. Next slide shows an animation of the sequence. We click the slide, yep. So the depot is the white dot and the blue dot is the servicer. The magenta line shows it doing its first Hohmann transfer to reach the orbit. The red line shows a phasing orbit. There's one shown here, but it can perform as many as it needs to. The green line shows that the two satellites are docked. It can stay docked for as long as it needs to. And then the second magenta line shows the second Hohmann transfer for the servicer to go back out into geo. Next slide. So this shows the requirements necessary from the client's perspective. So there's a wait time associated with the servicer reaching the depot, which is a function of initial angular separation between the depot and the servicer. So when these two satellites start the maneuvers, they have to be in the right alignment, and the time it takes to reach this is shown on this plot. The time ranges from about 0 to 27 days, so we can see that the average time before the client can reach our depot is about 14 days. The delta V required, on the other hand, is not a function of separation and is set at about 20 meters per second. Next slide. We'll now move into our system design. Next slide, please.
So here you can see our system requirement flow down. So starting at the top, we have our mission objective, which flow down to our L1 mission requirements and our L2 functional requirements, which then further flow down to our environmental and system performance requirements, which then go to our subsystem requirements. Next slide. Next slide, please. So here is our mission requirements. This is just a sample set, but our spacecraft will fully autonomously perform in-orbit refueling, component handoff, as well as resupply itself with no human interaction. Next slide, please. And then here is our functional requirements, which go down to what are engineering constraints. So we have designed for structural integrity with a safety factor of 1.4. We have bidirectional proximity communication, and our robotic arm will strictly be used for component handoff. Our propulsion system is designed for a full delta V with 20% contingencies and has a verification for a successful transfer. Next slide, please. So here is a CAD model of our fully deployed depot. Next slide. And then here you can see all of our components. Next slide, please. So here is the full size of our depot. Our hexagonal depot has a height of 3.57 meters and a side length of 3.51 meters and a fully spanned width of 16.26 meters. Next slide, please. So our depot is comprised of two bays. The payload bay holds all of our components as well as our avionics, and our fuel bay holds our fuel for ourselves for station keeping as well as our client refueling. We have a robotic arm at the top. We have a docking interface on all 6 sides, as well as 6 deployable solar arrays. Next slide, please. So here is our hydrazine refueling architecture, which is designed for reliability, scalability, and sustainability. So we'll be carrying 7,000 kilograms of hydrazine across 7 titanium alloy bladdered tanks. All of the tanks will be connected through a cross-feed ring for center of mass control and propellant transfer. The whole system will be pressurized by helium, which will be stored in 4 composite overwrap pressured vessels and will be designed as a closed loop system. And lastly, for our propellant management devices, we'll be using vane and screen type systems, which use capillary forces to guarantee a vapor-free fuel transfer to one of our 6 refueling interfaces. Next slide, please. So here is our refueling manifold. So starting on the left, the helium will travel through our burst disc and pressure regulator before it gets to the helium distribution manifold, which will then pressurize one of the hydrazine tanks. Hydrazine will then flow down to the commercial servicing manifold. Before it gets to the interface, it will go through a filter and a flow meter for cleanliness and accurate transfer accounting. Throughout the system, you'll see multiple isolation valves, which is used for fault tolerance. And then on the cross-feed ring, there is a vent and purge line for safe docking. And there are multiple temperature and pressure sensors throughout the system for system monitoring. And then for the closed loop helium system, when we refuel ourselves with the hydrazine, the helium will be displaced and it'll go back through the helium return manifold, where it'll go through a demister filter, then get stored in an accumulator, then compressed and cooled before returning back to the helium tanks. Next slide, please. So here is our propulsion architecture. So for orbit transfer and station keeping, we decided to use iodine-based electric propulsion. We'll be carrying 3,000 kilograms of iodine across 4 nickel alloy tanks with corrosion resistance coating. Since iodine is stored in solid state, we'll have a built-in vaporizer for all of our tanks to subliminate the iodine into a gaseous state, which will then be used for thrust. We also have 8 Hall effect thrusters, and the whole system is thermally driven, which maintain temperatures about 50 to 180 degrees for sublimation control. So here on the right, you can see the manifold of the iodine system. So it's sold in solid state, which then is heated into iodine gas. The gas then travels to the plasma chamber, which then accelerates as an ion beam for thrust. Next slide, please.
So now I'll be diving deeper into the types of components we have in our cargo bay. Firstly, we will have 3 truss antennas, which provide clients the ability to send and receive signals. These have a mass of 54 kilograms. Next, we have 30 battery replacement modules, which provide electrical energy for our clients, and these have a mass of 29 kilograms. And lastly, we have solar array replacement kits, which are based off of the ROSA class rollout wings. And these generate power for our clients and have a mass of 43 kilograms. On your right, you can see how our components are placed in our cargo bay. Next slide, please. This slide showcases our component handoff segment, or our robotic arm. Our robotic arm will have a total length of 4.55 meters with 7 segments of 0.65 meters. These calculations were determined through forward and inverse calculations. For forward and inverse kinematics. From this, we got a degrees of freedom of 7, which provides redundancy for our robotic arm to maneuver around our servicer. We will be using rigid segments that are made out of carbon fiber reinforced polymer due to its high stiffness to weight ratio. We will be using a soft malleable end effector and brushless DC motors at each joint. Next slide, please. This slide showcases our end effector. It will be using a cresting origami structure made up of aluminum panels and Capstone hinges. We chose a soft robotic structure because we wanted passive compliance for safely grasping our delicate components. For our sensors, we will be using a multitude of them, starting off with 2 cameras and 2 LEDs for illumination for long range depth perception from 10 meters down to 1 meter. And these will also help identify any fiducial markers on our components. For our mid-range, we'll be using time of flight LiDAR units, which provide millimeter accurate distance measurements through lasers. For our short range, or our final 10 centimeters of approach, we will be using short range proximity lasers, and these will also alert grippers to trigger a capture sequence. On our wrist, we'll be using a 6-axis force torque sensor, which will detect the forces that are being applied onto our components and ensure there is no structural overloading. And lastly, on our grippers, we'll be having thin film tactile slip sensors, which detect the shear forces on our components and ensure that if the component is slipping, our end effector will tighten its grip. Next slide, please. This slide showcases our communication architecture, where we will be using S-band to communicate down to Earth. We will be using X-band for any high rate data, such as videos and images. All data will be routed through a centralized command and data handling system, which will collect and packetize any onboard data. For any docking, refueling, and component transfer operations, we will be using proximity crosslink, which utilizes low latency communication. Next slide, please. This slide showcases our mass budget, where we see a majority of it coming from our propellant and our tanks. This we have a total system mass of 26,000 kilograms with a 25% margin. Next slide, please. Next slide. Okay, so for our propulsion budget, we see a majority of this coming from hardware, as you can see in the blue, but the majority of it will also be sellable hydrazine, as you can see in the yellow. Next slide, please. And this slide showcases our power budget, where we have a peak functionality of 17.3 kilowatts, our nominal functions taking 10.5 kilowatts, and our safe mode being 600 watts. Next slide, please. And this slide showcases our depot within Falcon Heavy's payload fairing, where you can see that our depot is within our volume constraint. During launch, our depot will be under severe dynamic loading, so we have some key design choices that we implemented, including having a centralized load path through the primary structure to the payload adapter, making sure our robotic arm is stowed when launching to minimize any dynamic loading, to have our propellant tanks structurally supported to withstand any launch loads, and to have a even or symmetric mass distribution to reduce any bending moments.
Next slide, please. Next slide. So we'll now discuss some of the trade studies that we use to reach our design decisions. So starting with our docking interface trade study, we had a few must-have criteria, including capability for mechanical docking, as well as fluid transfer. The primary metrics we considered were TRL and structural load capability, along with other metrics such as the number of partners that the company currently has. The main trade-off we observed was between TRL or heritage and performance. So for example, SpaceWorks' fuse blocks had excellent performance, but it has a lower TRL as it has not yet been demonstrated in space. So ultimately, we decided to take advantage of our 6-sided structure by placing 5 different refueling interfaces across the 6 sides. This will increase development complexity and cost, but it will allow us to appeal to the most number of clients. Next slide, please. So this slide shows the interfaces that we've selected. So we'll have 2 grips from OrbitFab, 1 ISI from iBoss, 1 fuse blocks from SpaceWorks, 1 link from Endurlock, and 1 PRM from Northrop Grumman. Next slide. For our depot propulsion system, the primary drivers were density and efficiency. So we decided to use electric propulsion because of its higher efficiency, lowering our propellant mass required. We saw in the mass budget that most of our mass was being taken up by propulsion. This was propellant, but also the hardware required to store that propellant. And so we realized that having a higher density propellant would enable us to have lower volume of fuel tanks and thus lower mass of those fuel tanks. And so the decision came down to xenon and iodine. Xenon has a much higher TRL. It's been widely used in space for EP, but it has a much lower density than iodine. And so we decided to use iodine as the propellant for our EP system. Next slide. Finally, for our robotic arm, the primary drivers for this were TRL and payload capacity. On the previous slide, we have our concepts that we considered. So we considered 3 different concepts for our robotic arm. These were all some combination of a custom or soft arm and a custom or soft end effector. We initially wanted to use a soft arm because it would enable precise maneuverability around docked satellites. However, this had a very low TRL and posed a risk of a wet noodle effect where the arm would flop around. And so we decided to raise the TRL by using a rigid arm, but we want to use a custom rigid arm where we can place the joints exactly where we need to still give us maneuverability around docked satellites. And then for the end effector, as we saw earlier, we're going to use soft robotics to reduce the risk of crushing a payload as we grab it, which would likely occur with a rigid end effector. Next slide.
Moving on to our risk analysis, we conducted our risk analysis to identify our mission and system level risks. We scored these risks on probability, detectability, and severity, and then placed them on our risk matrix to identify our major, moderate, and minor risks. On the next slide, I will go over some of our major and moderate risks and their mitigations. Our first major risk is potential propellant leaks or contamination during refueling. We plan to mitigate these risks using dual isolation valves and leak check propagation before transfer. We also risk radiation-induced degradation. We plan to use rad-tolerant parts and also additional shielding for critical components. We also need to make sure that we verify the module transfers to our clients. To do this, we will be using a redundant configuration of sensors. And lastly, we'll be using materials that demonstrate a strong resistance to thermal cycling and UV exposure. And then on our next slide.
You got 2 minutes left.
Thank you. We will be going into our interface control. This is what we require all of our clients to comply to. We'll be servicing 3 different classes of satellites. Class A, capable of docking, refueling, and handoff. Class B, capable of docking and refueling. And Class C, capable of docking and handoff. Clients that wish to refuel with us will need to have independent valves for refueling and share their tank telemetry with us. Clients that want to restock modules will need to be able to verify installation. On our next slide, we go into our development plan. Next slide, please. We identified what we would need in order to reach PDR, and this includes our vehicle integration. We chose SpaceX's Falcon Heavy as our launch vehicle. And we also need to perform some structural analysis and validate load cases, finalize our keep out zones, and design our resupply spacecrafts as well as finish our risk burn down. Next slide, please. For our technical paper, we plan to submit to SciTech's 2026 forum. This paper includes some analyses not presented today, such as our thermal and radiation analysis. This paper is about 20 pages long, includes a brief abstract and references. Next slide, please.
So moving on to our lessons learned, some of our most innovative concepts considered was the dual-use depot, combining refueling with robotic component handoff. We also explored a modular servicing architecture where our robotic arm could actually swap end effectors to support a wide range of servicing capabilities, but we ultimately went a different direction as it was too complex and would get limited use due to requiring our clients to be independently capable of rendezvous. And we also looked into a completely soft robotic arm utilizing Kresling geometry to have this octopus-like ultra maneuverability. On the next slide, we identify some key technology gaps that need to be addressed before the system can be feasible. First is large-scale iodine electric propulsion. It's been demonstrated in space, but never for systems of this scale. We also have to make sure we have closed-loop hydrazine tank pressurization, so recovering that helium is critical for efficient and safe refueling. Also, compact replacement modules, our solar arrays, battery modules, and antennas still aren't designed for easy in-space swapping. And then soft robotics, while they have been tested limitedly, they're still not space rated. As for our most
Unfortunately, we're at the end of the presentation time. Sorry about that. We got 4 minutes for questions from the room and online that we can go to.
Thank you.
Brian Newfer has his hand up in the chat.
Yeah, hi, Brian Newfer, Kennedy Space Center. So quick question about your hydrazine propellant tank. You said they were bladder, and then you also said they were PMD, so I'm just a little confused as to your style of tank you're planning to use.
We're planning to use the bladder tanks.
Okay, but then you mentioned vane PMDs. So where was that in your system, or was that just an artifact of an older design?
So that would be a part of just to move it through the tubing and stuff, to our refueling interface.
Yeah, just to clarify that the vanes would be part of the refueling manifold to actually transfer to our refueling interface. The tanks themselves would be using bladders.
Okay, I'm still a bit confused, but I don't want to take up all your time. Thanks.
Does anyone have any questions in the room?
Jacob Rome has his hand up online.
Yeah, I was just gonna ask, like, I know you spend 3 years to circularize your orbit because you want to be the most fuel efficient, but did you do a trade to say, like, if you wanted to get to the right orbit in 6 months instead of 3 years, like how much fuel would that cost?
Yeah, so we did look at that. One of our architecture options was just using hydrazine, because that would be a much faster burn time. But ultimately, the amount of fuel to require such a massive system to circularize that orbit would be almost as much fuel as we could possibly carry, meaning that we would have no hydrazine left over to sell. So we were kind of forced into the decision of using electric propulsion, and by still having at least 7,000 kilograms, that actually makes it realistic to generate revenue, even given that long transfer time.
Okay, thank you.
Did you do trades on the amount of additional plumbing you would need to get to those 6 different refueling interfaces versus just having one, and what your opportunity added is compared to that extra weight and complexity?
Yeah, so it definitely adds some complexity. We didn't do an official trade study on that, but the idea for this depot to be profitable and kind of actually enable the future servicing market, we wanted to accommodate that throughput. So it was most important to have at least 6 docking interfaces so we could support multiple clients at once. So that was something that we kind of accepted, the complexity that comes with that.
Hi, Bonaz. Your propellant pie chart went by real fast, but I saw RCS on there. Is the idea that you're only burning iodine, or can you actually use the hydrazine for things like RCS?
So our RCS would actually just be cold gas compressed, so we wouldn't be using iodine for that. That would just be kind of for the attitude control component. In addition to the RCS thrusters for more fine attitude, we actually we included reaction wheels as well.
Not about what we achieve, but about how we experience each moment. This is the most profound secret of life. Do a survey and let you guys just pick the ones you want.
Do we have any other questions? Okay, we have one more in the room.
Hi, this is Joe McGuire. On the slide that you put up for the different refueling interfaces that you researched and the TRL levels, is that just purely based off of research you were able to do online, or did you get any other data to be able to get to that summary of the TRLs that you showed?
Yeah, that was purely through research online. What we could find was available at the current time of design. We did reach out to several of the companies. So we actually had, for our design reviews, we had an engineer from Orbit Fab, engineer from SpaceWorks actually come in and talk to us. So we had meetings with them as well to kind of discuss those interfaces.
All right, thank you.
All right, thank you so much.
And next we have Bearcat assembly from University of Cincinnati.
All right. Are we good to go? All right. Thank you all for coming. Good afternoon. We are from the University of Cincinnati. We call ourselves Bearcat Assembly. My name is Diego Quevedo. This is Conrad Kent. We are presenting for our team about our design and ConOps for a self-assembled science station. Next slide, please. So our idea when we wanted to make something in space, we knew we wanted it to be in orbit. And so we thought about the things that you might want to make up there. And an idea that kept coming back in our brainstorming sessions was this idea that there's this looming threat that the International Space Station is going to go away in a few years. And so we were thinking, what exactly is lost when the ISS is gone? And an answer that would come up was that a lot of science capabilities would be lost with the loss of the ISS. And so that sort of borne out this idea that if we want to keep having the science that happens on board the ISS and combine that with this idea that we want to make something in space, make a new ISS. ISS was famously one of the first in-space assembled things out there. But if we wanted to do it in a new way, an autonomous way, what would that look like? And that's where we're sort of born it out. If you get the next slide, please, it'll flick. transition. And so the idea is that we want to combine in-space assembly. We want to combine this sort of already NASA funded and studied voxel armadas, we'll talk about that later, with the sort of commercial science that we sort of see on the ISS. Next slide, please. That sort of leads us into the idea of a persistent, autonomous, and reconfigurable self-assembling research station on orbit. Next slide, please. So this is our team. Again, we're 8 graduate students from the University of Cincinnati. If you go to the next slide, it'll have our program milestones. As you can see, we are behind on a number of things, but we still wanted to come and talk to you guys about our ideas because we think they're worthy, that they're interesting, and we're very passionate about them. And so if you go to the next slide, I am excited to start talking about the Armadas concept and what NASA has been doing in order to make sort of cellular structures in space with robotics. It was recommended by Cosmic to use such a structure, and we sort of ran with that idea. Okay, what can we make with this kind of this sort of structure? So if you go to the next slide, we take that idea and we try to marry a number of use cases or that is going to go away once the ISS goes away. And so one of them is the market for commercial science and Earth observation platforms. Originally, the idea for the station, the graduate student his task was to come up with an idea for a space observatory, and he sort of came back with this. We were like, oh, that wasn't the assignment, but it was kind of cool. The idea is that we'd have a number of these, we'd sort of make a structure out of these Armadas voxels, and then we'd come up with slots that science missions could go into. And we'd have a system in place in order to get things to and from their experimental bays. And so we're trying to meet a number of niches. ISS is a low Earth orbit, so what if we put it in geosynchronous Earth orbit? What if it's you don't have to have a dedicated payloads for your science mission, just like the ISS? And what if you're able to look at Earth and look at other things? We're trying to combine all of those ideas into this design. So if you go to the next slide, Conrad's going to start telling you about the concept of operations for the assembly.
Yeah, so the building block of our station are these Armadas voxels. We're using folding voxels. There's a study done by NASA Ames on these origami sort of flat pack voxels that could be made. We would have 3 different kinds in our station. We'd have structural voxels, which don't provide any other functionality. They just provide structure. We'd have data and power routing voxels that could make different DC power and data buses throughout our station. And we'd have solar panel voxels, which would be the same thing as the structural, just with a solar panel stuck on it and some sort of way to get power out of it. We'd also have cassettes where we could take all of those voxels and stack them together for launch and then remove one voxel at a time for assembly later on. Next slide. As far as our robotics, we would have our dual arm manipulator for the actual unpacking of our different components, as well as berthing our resupply vehicles. These would be similar to something like the Canadarm on ISS, and they would move around on circular rails outside of the core of the station, which the MISO concept also did, which I thought was funny. There's a video here, I think, in the middle. It's the 2 Armadas robots with the voxel. I don't know how to make that play. It'll play very slowly, but those are our assembly arms. So the external assembly arm is called Soli, and it moves the voxels into place, and then the internal arm goes up and bolts them together. That's part of the Armadas concept, like Diego talked about earlier. Then we have our actual station core, which would be made of a modified geosatellite bus that we would add places to connect the voxels to, as well as our different robotic components and a few other things. If you could go to the next slide. We analyzed 3 different kinds of experiments that could be put onto the station. On the path to PDR, we would reanalyze this and look at actual consumer needs and resize everything. But these are sort of our example payloads. We have small experiments that are the size of a 6U CubeSat. We have rad shielded experiments that are the size of a 12U CubeSat. And we have large experiments that are the size of the ArcAssist boson lockers. And the weights and power requirements are listed there. These would be sort of fused into their own voxel structures, and then we could connect those voxels to our station overall, so we could swap out different scientific experiments over the lifetime of the station. Next slide. So we would start with our launch. Everything needed for the first few years of the mission would be packed into the station core. It'd be launched on a rocket. We would deploy a temporary solar panel and our communications equipment, as well as some of our initial robotics. We would start the transfer up to GEO and begin the building process. Next slide. So over the course of a few months, we would build out these different pieces of our voxel structure. We would have rotator joints for our solar panel assemblies and build out our actual solar panels using the different assembly components. The dual arms will unpack one voxel at a time, hand the voxel to the small assembly robots, and the small assembly robots will bolt everything together. And that multi-step process takes a really long time, which is why it takes several months to actually put everything together. The robots also move very slowly. Next slide. The structure would be finished, we think, in maybe 5-6 months. We would connect the experiments to some of the wings of the station. The core of the station would always be pointed at Earth for Earth observation experiments and other things like that. In this concept of operations anyway, we could use the same overall structure and point it somewhere else if we needed to, but that has been our example mission. The robots would be passivated, and then experiments could go on while they're passivated to reduce our power usage. Next slide. And then we would get resupplied periodically, both for station keeping fuel for the actual propulsive elements of the core, as well as getting new experiments brought up. So when an experiment's done and when we want to start a new one, we can bring them up, unpack them from the resupply vehicle and stick them onto the station, and they can begin doing different science without having to launch an entirely new data and power system. We can also replace components as they go bad. The SOLI and MMICI, the assembly robots, those can be replaced directly. The dual arms would be a little more difficult to replace because they're stuck on the rails, but we could come up with some concepts for that in the future. Next slide. So why assembly is a big portion of this. The actual mission itself could probably be done just by deployables. The size of the solar panels we're looking at is not that big for deployable solar panels. But being able to swap out customer payloads and having the modularity and reconfigurability of the station core would add a lot to the mission itself. It's also a very constrained use case for the Irmada's concept, so we could put this together as a technology demonstrator for something that would strictly need to be assembled that would be large enough to require that. There are potential savings in volume and risk mitigation versus deployables. Very much potential. There are many, many more points of failure on something like this than something like a deployable solar panel, but we also have more options to address failures as they arise because everything is actuated. Next slide. Here is our animation. So yeah, that is the actual assembly process on the left, just building out the voxel structure. We would need to actually move the assembly robots past the rotating joints using our dual arms, and the dual arms can't reach the very ends of the station, which is why we need the additional little inchworming assembly arms. And then the animation of the operation is just the voxel being moved into place by one of the logistics arms, and then the internal assembly arm moving in and bolting it. All right, that's all for me.
Yeah. So when we talk about the impacts that this kind of mission would have, we sort of think about it of hitting two different major areas as well as where they overlap, and that's the impact on ISAM and the impact on space science research. So if you you can just hit next slide. Thank you. One more time. I knew I shouldn't have gotten fancy. Thank you so much. So the idea is that our ISAM impacts, we are primarily aligning with the National ISAM Implementation Plan and the National Strategy for ISAM, both published by the federal government, I believe the White House, in 2022. We are directly, supporting a number of things that come from both of those directives, including increasing the TRL level for autonomous assembly, flight qualifying structures like the armadas to be standard in-space assembly interfaces, as well as making a marker replacement for the ISS, something that's a bit concerned, and the administration, NASA, is considering a lot of commercial options, specifically for habitable space stations near Earth. Ours takes a different approach. So instead of focusing on keeping people in space, we're more focused on keeping science happening in orbit. And there's a number of ways that these two things overlap, obviously. This, like Conrad said, this is more or less a test case. Let's try to assemble something in space. Let's give it a purpose. And that will reduce the cost of future missions that want to use this kind of technology in kind of persistent platforms. As well as this would be a really great place in general for as a test bed for assessing technologies in the future. Next slide, please. This use case is our primary proposal, but we just also wanted to shout out the current sort of hot topic in space right now is the idea that we need to put data centers in space, whether it be for AI model training or some such. So this concept would ally itself fairly well to that kind of goal. So instead of being a research science station, you make the solar panels very, very large. You put it in the sun synchronous orbit that you would need to keep that thing powered all the time. And you would make a data center in space, but building it with the armadas and the robotics that go along with it. So next slide, please. So there's a number of things that you need to address to make sure that such a concept is feasible in practice. And so, some of the first things that we talked about was addressing the power and thermal needs. So our belief is that the number of experiments on board the station sort of limits or informs us how much power we would need to generate for our customers, and conversely, how much heat we would have to shunt for them. We're working under the requirement that we would need to supply a continuous 2,250 watts. And so we can add some padding onto that, say that we need about 3,000 watts from the solar panels. We make some assumptions about how many of the solar panels could be lit at a time. About 140 would sort of meet that 3,000 watt requirement. And the thermal assumptions we would make about the shunting abilities of the voxels leads us to having a requirement of 16.5 meters squared for thermal emissivity. Could you please, next slide? This is a bill of materials that explains how we're proposing we could fit all of this inside of a Falcon 9. There are the biggest components overall would be the propellant and avionics and the docking module, basically the main bus of the system as well as the arms. Overall, our understanding, our budgeting leads us to believe that the robotic arms is what would, on average, take up a lot of the power budget, which would lead us to, like I said, a power requirement of 2,250 watts and a mass requirement of 3,500 kilograms. Next slide, please. So to speak on the feasibility of autonomy, again, this isn't supposed to be teleoperated robotics. There's no astronauts up there. There's no one in Houston controlling these. So the idea would be that the robots on the station would be given basically orders, schematics, blueprints, and explained how to connect these things, and it would more or less handle it itself. So we have a number of concept operations that sort of explain how those blueprints would end up being, assembled in space, going from high level to low level. The animation on the left is from NASA, from a paper published about Armadas, but it shows you in a simulation sense how these things work together to assemble structures, which is essentially the same technology we would be exploiting for our station. So if you go to the next slide, please. This is the concept of operations, a simple concept of operations for how we would want the data and comms handling to work. We would exploit the currently used NASA tracking and data relay constellation, and to expect a consistent 50 megabits per second up and down. And we think this is important because we don't need to send commands very often to this station, but we would need to frequently receive information. Our customers, there'd be a number of them at the same time, and they would always want access to what's going on the station. And so it'd be really important to have a consistent channel of communication. Otherwise, customers would get very angry that they can't talk to what's going on up there. Next slide, please. I'm going to hand it back over to Conrad.
Yeah, so we analyzed a number of risks, both from a schedule perspective and from a technical perspective, and looked at mitigation strategies based on the risks that we identified. From a schedule perspective, we sort of just looked at what are the biggest unknowns about the concept in general and our technology gaps, and thought about ways to mitigate those. The general strategies would be for lower TRL. We would need to do some prototyping and heavy analysis prior to our actual PDR to figure out how much time we need to do the TRL raising, because there's a few big gaps there. For the technical risks, one of the biggest things is we are latching and unlatching a lot from different components of the station. So we need to make sure that we don't unlatch when we're not supposed to. So having latch detection at both the latch itself, but also at the joint level, grabbing onto something, trying to actuate the arm a little bit and making sure that it's actually latched every time we want to move something would be important. And then trying to recapture if we didn't latch it properly, which would add to our very long construction time, but would be very important to prevent us from releasing something from the station. Next slide. Here are just a couple of example risks. I don't think I need to go into any of these specifically, but we did an analysis on a wide variety of things based on all of the actions that our station would need to take over the course of its mission. Next slide. Here are three of the most interesting tech gaps to us and some of the most extreme tech gaps in our opinions. The robotic coordination would be very important, making these three different kinds of robots work together for a very complicated assembly mission. There are a few different NASA studies and other studies looking at taking the Armadas concept and looking at how they would actually move things around and put them together, and how they would move relative to each other. And it's still a big tech gap. None of it's actually been put into space, obviously. So that would be very interesting to look at. Smart decision making for attitude correction. We have two sort of competing pieces of the station. We have the experiments, which are very sensitive and need to look at specific points. And we also have a bunch of robots moving around on the outside of the station at the same time. So we'd need to make smart decisions about when to have the robots moving, when our attitude corrects for movements in the station, and when do we not correct. Because if we tried to cancel out every single motion of a robot, we would burn out our attitude correction very quickly. We also need data and power transfer between voxels to make up our different communications and power buses, which is a big gap that hasn't been addressed hardly at all. So we would need to figure out something for that. We considered pulling wires through the station, but because we have hundreds of solar panels and dozens of experiments, that would be very impractical. Next slide.
Got 2 minutes left.
Yes, sir. I'll try to hurry up. So in terms of advancing the high value missions, as I've already tried to highlight in the impacts, we believe there are basically 4 main components of what we are advancing here. Providing in-space services, flight qualifying ISAM hardware, developing autonomy in space, and improving the national scientific output as a major goal of this project. Next slide, please. There are a number of innovative concepts we've considered for this project, including the shorter crawling arms versus the dual arm rail system. We believe there's a number of ways you could reconfigure the autonomous robotics in here to optimize depending on your use case and what you need such a station to do. Next slide, please. There are a number of challenges, some organizational, some technical. One of them that I think is a fun challenge is the specifications. What Armada's voxels do is kind of up in the air. So when I would talk to the Armada's experts that Cosmic made available to us, they would say something along the lines, I'd say like, why, how much data, how much power can these theoretical voxels transfer? And they would say, I don't know. How much do you need? And so it's a challenge because we don't have an actual number to reference, but it's also an opportunity to help define exactly what this kind of hardware would require. Next slide, please. So there would be a long path to get to an actual PDR of this kind of project. It would probably start by assessing the customer needs, studying the cost, addressing the technical gaps that we've already addressed, and then iterating on the design and finally getting to the PDR. Next slide, please. So we do have a paper that we intend to submit for SciTech 2027. It has a lot more details that we couldn't cover in this presentation, so I'd recommend reading it. Next slide, please. And as a last note, one benefit of being comprised completely of graduate students is that none of us are leaving. We're all excited by this concept and want to continue working on it, possibly in other aspects, maybe try to get some funding for an actual demonstration of this kind of hardware. So if you go to the next slide, that should be the end and conclusion. So we've shown you our idea for an in-space assembled science station, or basically a market replacement for the International Space Station. We believe that though this concept is still high level, that it can be developed further and to make it an exciting and useful use case for in-space assembly. Last slide, or next slide, and that's it. Thank you all so much for listening.
Any questions in the room? I don't see any online right now.
I'm curious if your packing of the voxels was the flat pack sufficient to get a whole bunch of them in there and have it be mass limited as opposed to volume limited, or do they need to be stowed in a more compact way than that?
I think it still probably would be volume limited, not mass limited. The actual voxels themselves are really, really light. I think the original concept is that they would just be like tubes and joints, and then you'd sort of screw them together, but we decided our robots couldn't handle that. I think it would be better if they could get smaller, but I don't really see a way that they could get smaller without also making the robotics involved way more complex than just unfolding.
Yeah, I'd also like to say that the flat packing concept is ideal for our robotics, like Conrad said, but I believe that concept is just theoretical and something that would have to be tested. So another technology gap that we'd have to address.
Yeah, if we had 4 tech gaps, I would have included the actual cassette that needs to push the voxels out, dispense them, and then deploy them. It's not something that's been actually designed. So we need to figure that out.
Any other questions?
It looks like there's one on the chat. I can't read the start of it though.
Greenfield has hand up. You had a question?
Yeah.
Let's go with you.
I may have missed it during your presentation, but it seemed like the robots that kind of crawl out and build that voxel structure from the outside are what they're used to like build the structure initially. So I'm curious what those 2 arms on your main hub are for.
Yeah, I can
Yeah,
do that, or you go for it. Those are solely arms. They're part of the Armada's concept itself, so they're not something we designed. They come with the voxels. They're extremely capable for actually building out the voxels, but that's all they actually can do. They have a very limited set of degrees of freedom. So we would need arms for the actual unpacking operations, for moving things around the station, and for berthing resupply vehicles. So they wouldn't be able to handle those components. We actually thought about combining them all into like medium-sized arms that could inchworm around the station, but we decided to go with 2 sets of robotic arms instead.
I'll do one more question from Greenfield online.
Hey guys, this is kind of a follow-up related to Bo's question, but in the images that you had for the concept itself, were those able to be packed within one launch or within the volume of that mission, or did it need multiple launches?
Yeah, the design that we proposed, the idea is that you'd be able to fit all of that packed into a Falcon 9. Yes.
Yeah, they flat pack very small. I think we have like 700 voxels or something like that, maybe a little bit more, and they all fit very easily into that space.
Got it. Thanks.
All right. Thank you.
Thank you, everyone.
Thanks.
All right. Next up for our break at 3:30, we have Team Buckeyes from Ohio State. Is Team Buckeyes online or in person?
Online. Oh, we are online.
Okay, great. I'll start the 30-minute timer once you kick it off. Ready to go.
All right. Can everybody hear me okay?
Yeah, we got you.
Yeah. Hello, ladies and gentlemen. We are Team Buckeyes from OSU, here to present on our Capstone project, the Space Lab. Next slide, please. This slide includes our agenda, highlighting the different topics we'll be going through in this presentation. Everything from our milestones achieved to our path to PDR. Next slide, please. Pictured here is our team comprised of individuals with varying engineering backgrounds. Unfortunately, only 5 out of 6 of us are here to present today due to constraints with class times. Next slide, please. Here's a timeline highlighting our milestones achieved throughout the academic year. We started our project in August of 2025 and met our project manager in September. In October, we then narrowed the scope of our prototype and defined the requirements it must meet. We then completed our trade studies in November and finalized a conceptual design in December. Upon the new year, we started actually working on our prototype and spent majority of the second semester building it. The prototype was then finished by the end of March and validation was completed in April. Next slide, please. This is our executive summary, which shows the identified problem, our solution, the solution's impact, and the status of our current capstone. The fact is, textile-based materials are prone to tearing, and long space missions cannot always rely on Earth's resupply, especially if it's just for a patch. Our proposed solution is then to produce said textiles in microgravity on demand. This grants astronauts independence from Earth's resupplies and enables in-space repair. Regarding the status of our capstone, as said prior, the initial prototype has been finished along with its validation. Next slide, please. Delving deeper, space missions which have long duration tend to lead to wear and tear on all components, specifically textiles. Textiles are also relatively expensive to launch into orbit, so we determined that it would be much more cost efficient to simply produce the textiles within space. Next slide, please. In this table are 4 methods of textile production on Earth that we considered for our prototype. These include rapier weaving, non-woven, 3D printing, and linear electromagnetic weaving. We listed out differing pros and cons for each method. For example, rapier weaving, which requires high mechanical complexity control, but non-woven requires minimal. However, rapier weaving is much more proven, and non-woven will lead to weak fabric. For another example, 3D printing would be easiest to automate, but it would require significant power draw and it would prove to be quite slow. Next slide, please. In this table, we then listed out the requirements and user needs that were determined to be the most important for our prototype. Among these, we put special emphasis on reliability, crew safety, power consumption, as well as fabric quality. Next slide, please. So after taking those requirements and user needs, we then measured them against the 4 differing methods of textile production, which we saw earlier, using a weighted scoring system, with the 1 being the lowest and 5 being the highest. At the bottom of the table, you can see that rapier weaving came out with the highest score, and thus just determined our pathway moving forward. Next slide, please.
Fully functional system containing all of the subsystems that are required to complete each section of the threading operation. These are the required elements for that autonomous operation. The material feed system will be the spool holding the material thread, the mechanism guiding the thread, and the tension feedback control system, which is essential to the operation in microgravity environments. The weaving mechanism will contain all of the major moving mechanical components responsible for delivering the thread to the desired location, being the grabber hands and the rail systems to hand off the material. The fabric handling system, the fabric handling system, which was out of scope for our prototype, is in charge of cutting and stacking each of the inserted threads into the patch and threading the shedding properly. The electrical control system will be everything implemented with power and logic, being all the motors, both stepper and servo, microcontroller sensors, and receivers. The power system will take the input power and convert it to the proper directionality of the current and voltage for the electrical components mentioned before. Next slide, please. Here's a complete overview of a fully implemented systems operation. The thread is pulled from the spool with feedback tension using the grabber heads into the shedding, which is the alternating threads tangential from the insertion direction. The next part of the operation, highlighted with the dotted line, covers our prototype scope, which includes the rapier weft insertion, the grabber handoff, the pullback of the hands, and the rapier return from insertion. Out of scope, the next operations will be the beat up or moving the thread into the patch, cutting, changing the warp setting, which is alternating the threads, and cutting the thread into the patch. Next slide, please.
Yeah, so on this slide, we are showing a high-level overview of how the system is connected electrically, as power consumption is one of the main constraints we had to deal with when developing this prototype. As you can see from the top left, the power is supplied through 120 volts via any normal wall outlet. We then distribute that power to a 48 volt, 24 volt, and a 5 volt supply for our motors and logic controllers. In the bottom right here, you can see our logic controller acts as the main brain. It sends control signals to the motor drivers, as well as the grabbers, which support the rapier and other mechanisms. We also included infrared communication module in the bottom right there. This allows us to send control signals to the motor drivers, which then actuate the rapier and other systems. Overall, this diagram highlights how our systems, mechanical, electrical, and software all integrate together. Next slide, please. For our electrical prototype setup, one of the major focuses was cable routing and wire harness organization. We grouped wires into dedicated harnesses based on function, power lines, signal lines, and communication lines being a few of those examples. This was done mainly to reduce noise and improve reliability of the prototype. Routing was kept as clean and compact as possible by securing wiring along the frame and keeping the wires underneath the main moving components to avoid interference. And overall, the setup allowed us to create a system that is both functionable, testable, and scalable. Next slide, please. And this slide is kind of an overview of our rapier insertion mechanism we talked about earlier. Shown on the top right there is a red 3D printed part depicting our rapier insertion. In our design, we use the single rapier system to simplify the traditional double rapier approach. The rapier mechanism allows two bead grabbers utilizing linear guides to grab the material and move it out of the weft. For these, we use various linear guides, screw-driven and belt-driven. Those decisions were mainly driven by availability and the volume requirements we were trying to hit. Overall, this design was chosen to insert the thread reliability and while still achieving consistent thread insertion. Next slide, please. Here we have a prototype video. Sorry if it's a little bit skippy on our end. Overall, the video demonstrates right now the manual actuation of each of the servo motors and stepper motors. This overall validates our core concept, which is mechanical weft insertion, working in a controlled environment. While this is an early prototype, it shows a proof of functionality, and it provides a foundation for future system integration and more testing. Then next slide, please. Overall, the impact of this system is centered around enabling long missions, as Isaac stated earlier. By producing these textiles on demand, we can repair damaged materials in situ, like insulation or spacesuits, instead of relying on replacements provided from Earth directly. This can reduce our launch mass and our dependency on resupply missions. Additionally, the system is scalable, meaning that it can support future space missions and future space habitats. So overall, the main goal of this is to shift mission architecture away from a storage-based systems to more manufacturing-based systems in accordance with the Cosmic Challenge guidelines. Next slide, please. As we were trying to build this prototype, one of the main things we were focusing on is the feasibility. Our system, as we went through the trade studies, we chose the rapier weft insertion because it was a proven technology. It's been used for hundreds of years in commercial applications. So we're not entirely introducing a new method, we're just adapting this for this application. It also meets the key constraints of the bosun's locker. For this prototype itself, we were underneath 50 kilograms, and we estimate with a full implementation, we would still be well under the 400 kilogram limit. The estimated power was around 250 watts. We think that we could definitely scale this up non-linearly and kind of use the power more efficiently as we move into more a full-scale implementation of the prototype. The system also fits within the bosun's locker, that being the hardest constraint to hit, considering we are building a full manufacturing capability. Finally, as you can see on some of the images in the video we showed, it can be fully prototyped and tested on Earth using COTS components. So this gives us a realistic path towards flight readiness capability. Next slide.
So there's currently no system for textile manufacturing in space. Our innovation is adapting rapier weaving to work without gravity by redesigning the thread control and the thread handoff. So this, as Tyler mentioned before, this shifts missions from storing materials to manufacturing them on demand, which would also reduce payload. So while our design fits within the bosun's locker, it's also very scalable for future missions. Next slide, please. This slide shows how our system fits into a high-value mission. It advances in-space manufacturing by enabling textile production, which is a significant gap in manufacturing flexible materials in space. And it also improves mission self-sufficiency by allowing on-demand manufacturing instead of relying on Earth resupplies. So key applications of textiles in space include suit repair, thermal blanket maintenance, and fabric-based components like filters or cargo bags. Next slide, please. This is the storyboard for our system. So first, the system is launched within the bosun's locker, and then it is deployed on orbit within the initial system checks. And once commanded and received, the automated weaving process can begin, which would include yawn handling and rapier insertion. And then After that, once the process is done, the finished textile can be retrieved for immediate use or storage. This cycle can repeat throughout the mission, and it would enable autonomous on-demand manufacturing in space. Next slide, please. This is a risk matrix map, which sorts risk by probability and impact. It should be noted that the arrow on the left pointing up should say impact. The most critical risk include thread jams, power exceedance, and motor failure. Can stop operation entirely, while mid-level risk in yellow, like tension variation and handoff failure, mainly affect reliability and quality. And this matrix was useful to us because it helped us decide where we focused on our design. Next slide, please. So this table expands upon the risks talked about on the slide before by linking each to a cause and then a mitigation strategy. So lower risk issues like wear and sensor failure are addressed through robust design and component selection, while moderate risk like tension variation and thread jams are handled through control systems, while high risk issues like motor failure and power exceedance are mitigated primarily through power management. Next slide, please.
The way communication will be handled with our full system implementation will be through Wi-Fi on the space shuttle. The system will be designed to run autonomously with as little human input as possible, with full machine control to perform any functionality needed from the machine remotely. The only non-remote interaction with the machine would be inserting any additional raw materials if that runs out, or retrieving a finished patch, or any unexpected maintenance that may need to be done. And the need for maintenance will be notified to the user via the Wi-Fi transmission from a signal that gets sent out by the machine that's detected. For our prototype, an IR remote and receiver is used to imitate this Wi-Fi control to send operation and instructions to the machine remotely. Next slide, please. Some of the concepts that separate our design from already created industrial systems outside of the compact size and power constraints have to deal with microgravity. This includes systems such as the thread tensioner, which helps the system function independent of gravity forces, as well as the thread being well contained. When moving and cutting material, small particulates can be expelled, which in a microgravity environment can cause critical damage if debris is built up on critical components like sensors and motors. The modular design, for example, our prototype, presents proof of concept for individual subsystems of the machine. Next slide, please. Some gaps in technology that would be roadblocked in a full implementation would be accurately being able to research and assess a system such as textile manufacturing in microgravity. The constant tension control system will directly translate to the functionality and quality of the fabric, which our design aims to improve, as the fabric could be responsible for critical repairs. This also implies that the fabric should have a system that tests the fabric in order to perfect the creation and allow for improvements on the creation of the system. Next slide, please.
Yeah, so one of the biggest challenges we faced in the conception of this design was how we were going to be able to control the thread tension and microgravity. Without gravity, fibers can float, entangle, and cause issues within the mechanism. So this led us to focus heavily on tension control and clearly guided pathways for the feed material. Another challenge, as we listed earlier, was the volume constraint. This system had to fit within a very small launch volume. And so that required us to spend a lot of time thinking about how we want to prioritize the mechanical layout and where do we want to spend a lot of that volume for our design. We also encountered difficulties with a traditional double rapier handoff that is used on Earth and in industry. This requires very precise timing and alignment. It also uses up more volume. While it is faster, we decided to pivot towards a slower, more accurate single rapier insertion design to improve the reliability and future implementation of the design on the space shuttle. Next slide, please. So for our paper, we focus a lot more on the details of the mechanical design, electrical design. It's titled Orbital Weaving System for In-Space Manufacturing. We included about 18 pages of our design, our modeling, the prototype decisions, and the analysis that we conducted after the prototype was constructed. Some of the key sections that we want to kind of outline here is the ISAM relevance, what kind of trade studies, more in-depth trade studies we did to select concepts beyond just the rapier insertion mechanism. We also listed out some of our CAD models and how we prioritize the mechanical layout to fit within the bosun's locker, and how we plan to implement a control system architecture that can handle the thread tensioning mechanism. Some of the potential publication venues we want to focus on are aerospace and ISAM focused journals, as we are primarily a manufacturing capability. Overall, this paper serves as a technical record as well as a foundation for the future research and development that could be done to advance this capability. Next slide, please. And so I also want to talk about our path to PDR for a design review. One thing to note here is that PDR looks very different to various groups. The PDR in our capstone course here at OSU was different than what was defined in C3. So our path to PDR looks more like working towards a full prototype and a fully integrated system. And so in the near term, what we want to do is refine the rapier mechanism and improve the tension control reliability with an actual feedback control mechanism. Next, we want to integrate that into all of our subsystems, including the spool system and structural frame. And after integration and having a full system that can actually produce a textile, not only do we want to reevaluate for speed, fabric quality, and overall performance, but we would like to test this in an actual microgravity environment using maybe a parabolic flight or a low gravity simulator. As of right now, our low gravity tests are just turning the machine around in different orientations to validate that it works in all different orientations of Earth gravity. Overall, this structured approach would give us a clear path towards a complete and validated design ready for space flight. Next slide, please.
So building on that path to PDR, this slide focuses more on the refinement and validation of the full system, showing a proposed timeline. Once integration is complete, the next priority is improving overall system robustness. That means reducing failure modes, which for us are things like yarn misalignment, tension inconsistencies, and potential jamming in the rapier mechanism. We'll also be looking at optimizing the control system. Right now, we've demonstrated basic wireless control and operation, but moving forward, this would need to evolve into a more autonomous and fault-tolerant system that can operate reliably with minimal crew intervention. Another key area is testing in more representative environments. While our prototype validates the concepts, further testing, especially in reduced gravity conditions or high-fidelity simulations, would be critical to verifying the performance in actual mission scenarios. And finally, there's a strong emphasis on manufacturability and packaging, ensuring that the system remains compact, efficient, and compatible with spacecraft constraints while still maintaining precision and reliability. So overall, this stage is talking about a working system and taking a working system and turning it into something that is not just functional, but truly mission ready. Next slide, please. To wrap up, our system enables an on-demand textile manufacturing in space, which directly addresses the challenge of material degradation during long-duration missions. By shifting from preloaded textiles to raw materials, we can significantly reduce the launch mass and increase mission flexibility. This also improves crew safety and mission reliability, since damaged soft goods like insulation or suit materials can be repaired or replaced in situ rather than waiting on resupply. Ultimately, this project contributes to the broader goal of in-space manufacturing and self-sustaining missions, which are essential for future space stations and deep space exploration. Next slide, please. Thank you for watching our presentation. We'd be happy to take any questions you may have.
Any questions? Got one in the room?
So when this device is up in orbit or in space, I assume you still have to get the raw materials up there. So what would be the advantages of manufacturing in space as compared to manufacturing finished material and equipment on Earth and sending it up with the initial launch?
Yeah, I can hit that question. So I think this provides us with more flexibility. So say, you might want to provide, so that material might be manufactured in certain size quantities on Earth. And then when we go up into space, it may be used to repair suits, but you'd be wasting that material if, say, the repair only needed a certain amount. So this allows more flexibility and more efficient use of the material that would be sent up on space. So it's all about efficiency and kind of allowing for more flexibility than what a traditional system would allow for. Does anybody else have anything to add to that?
I would say yeah, because I guess to build on top of that, you might not know exactly what you need out in space. So it is nice to have a system that can make that textile into what you might need. Because for instance, you might have gotten a lot of one kind of shipment out into space, but if you ran out of that specific one, it would be nice to have extra yarn and textiles to build some using the system.
We got a question online. Apologies if I missed this, but how do you plan to measure the thread tension during the manufacturing process?
Yeah, so this is outlined more in our paper. The thread control mechanism, we did not get to fully implement in the prototype, but essentially it would use, it's a mechanism that is commonly used in loom systems down here on Earth. Essentially, it uses a rotary encoder and additional rotary springs to assess deflection in a rotary device. And that deflection would read back as a tension along the string for the device. So we planned on implementing that. It's been proven to work in other systems as well.
Any other questions? If not, oh, we got one more from Bo.
What is the kind of production rate that comes out of this, and how long would you need it to be for example, on a zero-G flight to be able to test it in zero gravity?
So you're asking how long it would take to get this to a mission-ready platform?
Like what's the duration of the test that would be useful? Is zero-G flight enough, or would you need like a suborbital flight?
I think realistically, a zero-G flight could do it. Testing on something like the Vomit Comet could work pretty effectively for testing and proving that it works in zero-G environments. Having, say, time less than a minute could demonstrate that the mechanism is working properly. Larger actual manufacturing work, though, our current system is running a bit slower to ensure accuracy with it. And so a system like that might, to demonstrate it longer, might actually take longer orbital flights because it will need to run in the range of maybe 10 to 30 minutes to kind of really demonstrate and get a system that works.
All right, well, if we have no more questions, we got a 15-minute break until 3:45, and then we'll pick it back up with PackNanoSat from NC State.
Hey, just a heads up, we're not getting any audio from the room. So if somebody can check that mic at the podium, that would be great. Thank you, guys.
You do it.
Checking.
We can hear you.
Oh, you're giving. All right, cool. All right. Fire. Yeah.
All right, PackNanoSat, you can get started.
Hi, everyone. We are PackNanoSat from North Carolina State University, and our project is orbital refueling by internal tank transfer. Next slide. Today, we're going to be going over a little bit about our mission overview and some of the analyses we took when looking at our orbit and everything. And then we're going to start looking at our subsystems and start looking at how each subsystem worked towards completing the project. And then finally, we're going to cover the risk and innovation and then move towards our path forward. Next slide. I'm Mason Stymack. I'm the project manager.
My name is Nick Lawton. I'm the docking system and interface lead.
I'm Will Bussey. I'm the track system and tank design lead.
My name's Colby Harrell. I'm the mission analysis lead.
I'm Aiden Hayes, and I was in charge of the docking port design.
And our advisor, Felix Awari. Next slide. Next. Yeah. So for executive summary, the problem we identified was there's not a current method for in-orbit refueling for client satellites. So we realized, especially in LEO, there's a high opportunity for adding a lot of delta V to these missions without a large cost of delta V for RPOing with these satellites. And the solution we came up with was a replaceable propellant tank with a track-based internal transfer system that uses a slightly modified IDS standard docking system to allow for a modular replacement with client satellites. And then with our system, we have 18 ORUs to allow for 18 different clients we can service. And the impact we're hoping to achieve is autonomous satellite refueling. We're hoping that we can extend mission lifetimes while also limiting the accumulation of orbital debris, and then enable modular ICM architecture for future missions. And then the current status of our project is we are in the final CAD design and then moving towards initial prototyping and still waiting on components so we can start building our prototype. Next slide. So a little bit about the milestones we hit. So in August, we selected our program manager or project manager. And then over that whole semester, we worked on designing our capability we wanted to focus on refueling. And then we started going over system requirements, trade studies, and then moved towards our system requirements review. And then at the start of this whole past semester, we've been working towards finalizing our conceptual design and then moving towards the PDR and then prototype and final stages. Next slide, please. So we're hoping to advance high-value missions by supporting on-orbit servicing and refueling. This is a big thing for demonstrating a practical way for satellites to extend their lifetime or potential deorbiting service, a way to not limit the amount of time you have in space with your mission. We're hoping to advance modular design also, because if you can find some way to allow many satellites to use a modular design, it's a lot easier to implement a lot of different projects everyone wants to try and help with client satellite servicing. We're hoping to make scalable ICM infrastructure. This could help with, as LEO gets more populated in these other orbits, when more constellations and just more development occurs, having a scalable infrastructure makes everything a lot easier. And then leveraging existing host platforms. So on the right, here's the Espastar platform is the one we chose to use. This one has many bays that we can do a proof of concept with our design. Next slide. So the impact we're hoping to achieve is, one, extending satellite mission lifetime. This is with providing a delta V increase, as well as hopefully delaying field limited end of life causes. We're hoping to reduce the need for, or reduce the cost and launch demand with the ability to refuel a satellite versus relaunching a satellite. There's potential to save a lot more money and a lot less investment in designing a completely new satellite. Enable scalable servicing. This is very helpful for servicing multiple clients that have this capability or need the certain idea you're proposing. And then finally, the big thing is reducing orbital debris. If we can give potential deorbiting services or life extension services, we have the ability to reduce the amount of orbital debris accumulation, especially in LEO. Next slide. Thanks.
All right. So this is our concept of operations. This is going to be a high-level multi-phase expectation of what we expect our project to be. So in phase one, we're going to have the client relaying the need for refueling. The ESPA will be notified, and then the rendezvous and proximity operations will be calculated. In phase two, we're going to have that the RPO is then conducted, client and ESPA will dock, and then the refueling will commence. And in phase three, we have that the refueling is done, and the ESPA will undock with the client, and the client will return to its original orbit. Next slide. So here is a flow diagram of our expected ESPA specific mission plan. So in the task one in the top left, we have that refueling is requested. After that, the RPO is determined and then conducted, and then the ESPA will dock with the client. The track system will then replace the ORU. After that, the refueling is done, the satellites will undock, and then we get to our decision here in the flow diagram. If the tanks are depleted on the or not depleted on the ESPA, then the ESPA will return to task one and keep cycling through. If the tanks are depleted, then the ESPA will deorbit after its mission. Next slide. All right, so here is kind of this is the animation of our refueling sequence. This is kind of like the going in depth about the phase two of our ConOps. On the left here, or on the right, is the client satellite. On the left is the ESPA. As you can see, they dock here. The orange tank represents the empty fuel tank from the client, and the green tank represents the replaceable fuel tank from the ESPA. Next slide. And this is a side view. Here you see they dock. We have the linear rail transferring the tanks, and then we have the rotary drum switching over the tank into the new one to then transfer into the client. Next slide. All right, so here's our requirements and orbit selection. So we had two main operational requirements in the past few months. The first one being that the ESPA ORU shall lengthen a client satellite by 5 years. And the second one being that the ESPA shall prevent orbital debris accumulation by 1 satellite per servicing. However, one thing to make note of is what's called the 5-year countdown rule. This is a proposal initiated somewhat recently by the FCC, stating that if you launch a satellite, it has to have the capability to deorbit within 5 years. This is an important goal to consider when doing this project, because if we can verify and validate that our project or our product can, keep things not being orbital debris in space, then measures like that can potentially be reevaluated. So what we targeted in LEO was the sun synchronous orbits in the LEO range, particularly around 800 kilometers. We chose this range because of it's highly populated with satellites that are used for imaging, tracking, and Earth observations. There's less delta V needed for RPOs if you have no general plane change. So this means that we want the ESPA to be in a parked orbit within the same inclination band as these client satellites. Additionally, the satellites and tank sizes are actually comparable to what our nominal design solutions are anyways. And at 800 kilometers, there's lower impacts of drag, meaning that will help the ESPA benefit with lower station keeping. Next slide. Here we have some of our reference satellites. In particular, that's the EO1, the Calypso, and the ESMOS. And then we have some general reference parameters seen here, like total mass, the type of thruster used, and then the delta V that would be given through a refueling service. However, the one we want to point out is in green, the EO1. We chose, and looking at its general parameters here, you can see it's a relatively small satellite, low mass, but in particular, it received the highest delta V boost through our proposed refueling service. But additionally, and another benefit is it just also had a bunch of publicly accessible information, which is always nice to work with. Next slide. So an interesting approach we wanted to have is not only show the technical aspect of our design, but then also to approach it economically and see whether or not this would even be feasible or if clients would want to even use the service. So with everything included, we have an estimated launch weight of around 1,350 kilograms. Looking at different rideshare programs, we saw that the Falcon 9 had a launch cost of around $74 million with a payload capacity of around 23,000 kilograms. If we assume a linear cost relationship between the cost and the size, that means this rideshare would actually be around $3,250 per kilogram that you launch. That means our launch cost would be around $4.4 million. And if we assume that there's 18 tanks that are going to be replaced by the ESPA, that means we would charge $250,000 per refueling to break even. And then for these highly specialized servicing, contractors will typically mark it up by around 40%. So we would need to charge $350,000. And thankfully, but because of the EO1's publicly accessible information, the EO1 launch cost on average is around $2.3 million, meaning that based on this rudimentary economic analysis, that refueling client satellites would actually be around 85% cheaper than just launching another EO1 satellite. And additionally, some important things to consider is the end of life. Our revenue would be around 6.3 million, meaning that we could then launch another ESPISTAR because we've made profit. And additionally, part of our goal is to reduce or mitigate orbital debris. So we would actually be able to deorbit the ESPISTAR after its mission is over. Next slide.
All right, so now I'm going to go over our docking mechanism design. So this design should look familiar if you're familiar with NASA's docking system, because that's what it's inspired by. It is a 3-arm compliant capture mechanism that is designed to fit nicely with our orbital refueling unit. And it consists of a female and male docking port. So this is a much more simplified version of NASA's docking system that is compliant with the International Docking System Standard. So the phases of capture are soft capture, where the 3 flaps will open. The client satellite will be guided in using alignment guides. And then there's alignment pins, which are directly taken from the IDSS. And then we have some springs. They're a little hard to see, but there are some spring damping mechanisms that will ensure, to mitigate the risk of damaging either the client satellite or the ESPISTAR platform. And then the hard capture phase is where those flaps will then come down onto the client satellite and create a hard lock. So the reason we're able to simplify this design so much is we're not pressurizing it. We're just going to be pulling tanks between our ESPISTAR and the client satellite, which allows us to make a much simpler design, which should be a lot cheaper for client satellites to then use in their own satellites. Next slide, please.
Moving forward, we can see what we expect the client satellite would require for their plumbing system to interface with the tank ORU. We selected hydraulic quick connect fittings to achieve the interface between the tank and the client satellite. We'll go over the actuation of the outer jacket on the female side on the next slide. But for now, before detachment, we would close the solenoid run valve that is directly after the quick coupler. And then we've also additionally put in a flow control valve with a pressure transducer and a feedback loop to ensure that we can monitor the mass flow of hydrazine going into the client satellite's propulsion system. And then finally, we'll have a check valve for safety. And all of these parts are out of 316 stainless steel to be compatible with hydrazine. Next slide, please. And here you can see the quick coupler actuator plate. This will sit on the outside, basically be a cuff around the female side of the quick coupler fitting. And in the middle picture, you can actually see square cutouts on the top and bottom of this actuator plate that linear motors are going to be pushing forward. The internal spring inside of the female side of the quick coupling fitting will return the system to a nominal locked position. And I don't think I mentioned on the previous slide, these are auto sealing fittings because they're used with hydraulic systems. So upon detachment, that tank would be closed. And there's also, you can see 4 holes in this plate. Those are for linear guide rails to ensure that we can keep up the longevity of the linear actuators and the quick coupler itself. Next slide, please. And here you can see what we expect the electronic interface and data transfer to look like between the client satellite and the ESPISTAR. We are also moving forward with the IDSS compliant or International Docking System Standard for the electronic bulkheads between the male and the female sides. We won't need as many pins as NASA does on the ISS. As you can see on the bottom left picture, that's typically how many pins they have in their connector. We won't need nearly that many. We'll need about 20, if even that. And moving forward to the data budget on the right-hand side, this is rudimentary data budget based on our motors, our sensors, and what we expect our data handling to be. And that equals 33 bytes per response update. So at a 10 hertz frequency, we would be hitting 2.6 kilobits per second, and using UART, we would easily be able to hit that because it can hit 115 kilobits per second. Next slide, please. And finally, this is the required electronics design for the client satellite to have. This is actually the prototype design. So this is the non-mature design. The schematic that you see in the middle will be pretty much the same for the mature design, just the hardware selection will be different. We're expecting to use a ESP32 CAM module. We're currently building out the prototype right now. And we're going to use some I2C hardware as well to actuate the motors and the sensors. Next slide, please.
So here you can see the actual design of the rotary ORU that we've been talking about. And the main design concept behind this is that you've got sort of an outer shell that stays static and mounted to the Espistar, as well as the docking mechanism that is also static against the client. And what this means is that sort of all of the electronics and everything important and structurally significant gets to stay statically sound, while the internal drum that contains the tanks rotates, as you can see in the top right. And that allows us to align empty tanks with empty bays and full tanks with the now open linear rail to go into the client satellite. As you can see pointed by the red arrows, the tanks are actually sitting on linear rails and they're firmly attached to those rails. And that's what allows them to smoothly translate between both the Espistar and the client satellite. And the main thing that will push them is sort of like a crawler that's going to sit on the linear rail, which we'll discuss later. And then the main design approach of this system is to try and make sort of storage of fuels and then the transfer of those fuel tanks as minimally complex as possible. And doing it in this rotary fashion ensures that we only have 2 degrees of freedom in this system, one being the rotation of the system itself, and then the linear translation of the tanks, which drastically reduces the amount of complex mechanisms we need to include. Next slide. Here you can see a quick trade study. We'll go more in depth on this later about the different types of mechanisms that we considered. But just know the main takeaway of this is that we chose the rotary design due to its mechanical simplicity over something like a robotic arm or a shipping container, which is more like a pick and place system. Next slide, please. Here you can see the actual design of the tanks themselves, as well as sort of how we're going to do some of the hardware in the back end of the rotary RU. As you can see the call out on the right. The tanks themselves are 83 centimeter cylinders. They're long, and then they have 21 centimeter diameter spherical end caps. And then with a wall thickness of about 0.5 centimeter, you've got a total internal tank volume of around 30 or so liters. And this is exactly how much we need to refuel those satellites that are around 600 kilograms in weight. And then moving to the right where you're looking at the actual hardware, you can see that number 1 here is the brushless DC motor. That's actually going to be the main workhorse that's going to rotate that internal drum with all the fuel tanks. And then number 2, if you click next real quick, is the space for the hardware where we're going to mount the electronics, any motor controllers, electronics housings, everything that you need to actually operate the satellite. And then lastly, number 3 is a reflective optical encoder. And this is going to ensure that the orientation of the fuel tank is perfectly aligned with that client satellite to ensure that there's no issues with the tank moving onto the client satellite. And the reflective nature of that encoder is to make sure that all of our electronics can stay situated statically on the client or on the Espistar side of the ORU. Next slide, please. Here's a quick trade study that we did for which material we were going to use at the tanks. Based off of our configuration and then giving a factor of safety of 2 to our total hydrazine storage pressure, we know that our material needs to withstand 100 megapascals of hoop stress and 500 megapascals of longitudinal stress, just because of how long our tank is. And then based off of these numbers and also industry usage and its ease of manufacturability, we went with our titanium alloy as seen above and in that first column. Next slide, please. And lastly, here's our very early prototype development of that tank crawler concept. As you can see, the main idea here is that it's also situated on that linear rail and it'd be behind the tank. The main idea is that it's going to be something small and easily manufacturable, something that will have like a housing and then have a servo motor or 2 that will have gears that can run along gear mesh. And what this allows us to do is mount it to the linear rail and put it on each linear rail. So then the only commands that you need to input into it is simply forward and backward. The main idea is that this gear will mesh with a sort of rack gear that goes along the entire length of the linear rail. And that will allow it to sort of like mesh and just continue motion along the entire length of that linear rail. In the current state of that CAD, you can see it's very loose, and that's a very prototype type view of that system. In the space grade sort of adaptation, you're going to have sort of like a boxed system that's more clamped down onto that linear rail, and that you'll see that rack gear is more integrated into the rail itself. Next slide, please.
All right, so once we're docked, the idea is that our system will operate largely autonomously, which means minimal connection to the ground. So we're doing this by only transmitting data that has a low data rate, things like the docking and transfer status, the ORU's position, and pressure and valve states. So this allows us to operate with a link margin well above what would be required. It gives us a lot of play so that this system can operate autonomously. Next slide. So here are some of our most important technology gaps. The couple ones that I'll go over are the docking and mechanical interface, which we identified to be at a TRL around 5 to 6. And that's because it is a design that's based off of NASA's own docking system. So it's been proven to be used. We've just created a much simplified version of it. Something else would be our ORU transfer system. So this is relatively new. It's an experimental proof of concept, and we'll need to prototype it and then test it in a relevant environment in order to make sure that it will be qualified for use. Next slide. And so here are some of our risks. The main risk is damage to either the ESPA platform or our client satellite. God forbid we would create any more debris in the low Earth orbit. That would completely ruin the point of this mission. So some of the mitigation we're doing is alignment guides and tolerances, building in a lot of redundant latching for the docking and a safe mode when docking to make sure that if there's any sort of misalignment, we can safely abort before any damage would occur. Next slide. And here's some of our most innovative concepts that we considered. So we considered originally a robotic arm transfer system, but we wanted to use the ESPA platform. And there were 6 bays, as you saw earlier. And so putting a robotic arm in each of the 6 bays wasn't really feasible, and it added a lot of complexity. So we eventually decided to go with our track system. We also looked at direct fluid transfer, but that creates a lot of complexity and creates a lot of risk for things like contamination, sealing complexity. So this tank system is very simple. It's kind of a plug and play system that would be really easy for client satellites to adapt to. And then lastly, we considered a container style transfer mechanism. You can think of this as being like how a 3D printer moves in the X and Y direction to, pick up a tank, place a new tank in. And we ended up going with our rotary system and our linear system because that's only 2 degrees of freedom, whereas this would be 3 or more. So those are some of our innovative concepts. Next slide.
Got 3 minutes left.
So some of the biggest challenges we encountered while working on this project, one was working on the rotary transfer system. So because of the alignment has to be so precise between the client satellite and the ESPA, if those linear rails aren't perfectly aligned, then one, there could be a fault between the two, they could get stuck, or even worse, it could be a catastrophic failure. So the big thing was we had to find a way to ensure that it was going to be very precise. And what we came up with was the optical encoder between to ensure that wherever that linear rail placement is, it will line up perfectly with where the client satellite's linear rail is located. The docking and interface, we had to find a way that allowed clients to implement an easy interface. And so we came up with the IDS standard, or a modification of that. So by using something that's proven, I think clients are more likely to want to use something like that with just a slight modification that allows for the transfer of the ORU. And then one of our biggest issues was team continuity and the project transition. So at the end of, we're a new club, so this was kind of our initial project starting. So at the end of last semester, we lost about 2/3 of our initial team. So the issue was kind of starting over again at the beginning of the semester, finding new team leads and making sure a lot of the information we worked with that whole semester was not just gone like it did. So making sure that all the responsibilities are prioritized and making sure there are a lot of places where data is stored and just communication. Next slide. So for our paper, there's some just kind of characteristics about it, and we're thinking of publishing in the IAA, either SciTech or student conference. Next slide. So kind of our path to the PDR, one thing we need to think about is reassessing the platform compatibility. The ESPA we designed around the largest bay in the ESPA. So if we have any modifications to maybe the docking system or externally, we might be outside of the bay ranges of those smaller ones. So we might need to reevaluate if this is a good platform for us to use. We also need to look forward and start validating our functions, such as the rotary mechanism, the transfer mechanism, making sure tank retention, the crawlers, and all those concepts. And then finally, working towards validating our final requirements and working towards the PDR. Next slide. And then kind of just conclusion. So the problem we addressed was there's no current capability for in-orbit refueling. So the solution we're proposing is a modular in-orbit ORU tank exchange system that uses a track-based with a modification of a used docking system. And our method uses 18 ORU so we can service multiple client satellites. Some of the big lessons we learned is keeping like the simplicity and the scope of our project. Initially, we started very broad with what we were trying to do, and we kind of realized we needed to scale it down to be able to achieve what we wanted to in the time we had. And then finally, like looking forward, we need to start working on our prototype, validating all of our designs, and then kind of integration. Next slide. Yep.
Questions?
Brian Newfer has his hand up online.
Go ahead, Brian.
Yeah, hi, I'm Brian Newfer from KSC. So when you are doing your connection between the tank and the system, is there a valve that isolates the bulk propellant from the tank from the QD, or is essentially the QD hot with liquid propellant?
So the QC is going to be hot with the propellant. Sorry, the QC is going to be hot with the propellant, but since we actually originally chose a non-hydraulic quick coupling fitting, and that not all quick coupling fittings are auto sealing. So that was something that we really had to consider after we had made our initial choices. We realized that if we undock, propellant's just going to be spraying right out of the tank. So we moved into an auto sealing hydraulic quick coupling fitting, if that answers your question.
Yeah, I think it does, but I think that precludes you from from checking the interface before you flow liquid in through the system, which is a pretty important requirement to make sure that there's not some issue with the seal that leaks all your propellant out. Something to
So would
consider.
you recommend just having an isolation run valve prior to that
Yes.
quick coupling fitting? Okay.
Yes,
Yeah.
and then an ability to leak check that seal after you do the QD mate. So is the more practical solution.
Okay. Yeah. Thank you.
Yep. Thanks. Good job, by the way.
Thank you.
Greg Richard. Go ahead in the room.
All right, so I commend you guys for putting dollar signs up on the slide. Did you consider how satellite production, development of your technologies, development of your ground system, operations would factor into those numbers?
Yeah, so this was just, again, so it's a rudimentary economic analysis. So it's essentially just like an isolated system of just the launches. So yes, all the other stuff exists, right? You'd if you were to like launch a new satellite, you'd have to build that satellite. In the case, like, you know, we need a ground station that talks, so you'd have to have a ground station in place or build a ground station. But no, just for our economic analysis, it was just an isolated view of just the launches. But additionally, we are a club. We're not a group of seniors, for example. So we had not to throw anyone under the bus, but we had a freshman on our team who's really interested in space, and our only way to think about including him into our work was, okay, you could potentially look at the economic feasibility. And I worked with him in terms of guiding how exactly we would do that, and we thought about isolating the launch cost.
Okay.
But yes, we do recognize that the other systems are in place. Yes. Thank you for your comment.
Greg Richardson has his hand up online.
So I really like this idea from a servicing perspective and how it simplifies the interface. But on the client side, most of the prop tanks are on the interior of the spacecraft, which keeps the CG fairly stable as propellant gets depleted. But this requires external access to that tank. Did you look at the client side impacts of having tanks that have that kind of external accessibility?
Yes, so the acceptability itself is something we definitely looked at, and it's something we sort of analyzed in terms of having like a closing bay on the outside. But the main idea of this is that when the client satellite docks, the linear rail that connects the internal rotating ORU and the client is very, very close. And so that crawler that I was mentioning earlier in the slides is actually able to traverse all the way into the client satellite. So this would mean that the client satellite could have some sort of opening bay, but the actual internal location of the fuel tank would be very similar to where you would have it on a traditional satellite in sort of like in construction nowadays. And so our sort of approach to this project, at least, is having like a standardized like mounting system for your fuel tank when you end up sending your satellite up. And this means that when you sort of open up your docking bay that includes your propellant tank, you can mate, and it'll be like almost like a surface to surface dock on the client satellite, and then your propellant will sort of maintain its same like location relative to its CG. If that answers your question.
Thank you.
We have a question in the room.
So I saw that you guys are targeting LEO. Is there any like market analysis that you guys have done instead of like targeting other like MEO or GEO? Just because from what I understand is that most satellites in LEO, they'd rather just more be replaced instead of actually being serviced.
I think the big thing we looked at, especially for like MEO example, there's probably like a rough number, there's probably like 250 satellites in orbit in MEO, maybe less. So I think the delta V required to RPO with those satellites would be way beyond what's capable with the ESPA-STAR, especially if we're targeting 18 clients to service. With the delta V needed to, assuming we're not going to require them to come all the way to us, and we're going to have to meet them some mission step, I just don't think it would be feasible to service that many client satellites at that kind of required delta V. And even further with GEO, like the required change in all your delta V would be pretty large compared to what we have available.
All right, thanks, guys. Well, all right, next step. Oh, I'm gonna picture. Well, there.
Wait, you gotta switch over because I'm like in the frame for the video. Flip over. Thank you. Okay, good. Perfect, thank you.
All right, next up we got VT Luna from Virginia Tech. I will start the timer whenever you guys kick it off.
All right. All right, good afternoon, everyone. We are Team VT Luna. We are focused on Track 2, Lunar Operations, and this is Project Hesia. Next slide, please. And this is our team organization chart. I'm going to go ahead and introduce everyone, starting with our advisor, Dr. Shinpal, and our mentor, Dr. Pines. My name is Abhinav Katka. We have Nick Harvey, Ty Brennan, Tim Curry, Juliana Evans, Jonah Bradley, Ada Bellicano, Duncan Foster, Braden Peterson, Hugh Young, and Robert Higginbottom. Next slide, please.
So, in order to complete our C3 track of creating lunar infrastructure, we first had to decide what sort of infrastructure do we want to create? And to answer that question, we asked, what problems can lunar infrastructure potentially solve? And what we decided to focus on was the problem of the rocket plume of landers disrupting regolith, which can then kick back and damage that lander. Hardware damage to landers can potentially be dangerous and even mission ending. Hence the problem as we plan on launching many more missions to the moon in the near future. VT Luna proposes the construction of landing pads in order to mitigate this problem. We plan to do so by using a multi-system payload capable of creating landing pad tiles and assembling them. which will reduce the risk. Landing pads offer a flat and strong surface without lunar regolith dust that hence will not be kicked back to damage the lander. So far, we have developed a concept for a payload and a mission concept in order to address this problem. And we have also begun early prototyping of our rover system, which we will talk about shortly.
All right, next slide, please. All right, so the scope of our project, we want to produce structurally and thermally sound tiles that can be repeatedly fabricated. We wish to test these tiles in situ on site using the resources available to us. And we also want to recover tiles and ship them back to Earth for further testing here on Earth. And then we want to assemble tiles and test configurations on the lunar surface. And we want to make sure it's scalable to increase production in order to make larger launch pads and also determine feasibility of the overall system. Our time frame, we look to launch by September of 29 and utilize the system as soon as it lands, and then the mission will end in March of 2030. Our assumptions, there'll be an astronaut on site to manipulate some tiles and also to ship them back. Almost constant illumination of the landing site for 6 months, and the ability to utilize all features of the lunar Griffin lander. Key requirements, we have to keep under the 200 kilogram mass budget, occupy volume of less than 1.5 by 1.5 by 2.5 meters, and be able to autonomously manufacture structurally sound tiles.
Next slide, please. Okay, so this is advancing high-value mission objectives. So a successful demonstration of our mission, Project Hestia, would directly advance the goals of NASA's Moon to Mars architecture, specifically highlighting 4 primary objectives outlined by NASA's architecture. The first of these is physics and physical science. The completion of our tile testing objectives would offer humanity a deeper understanding of the properties of lunar regolith and its potential role as a construction material in further lunar infrastructure, which leads us to our second, lunar infrastructure. This is the one that landing pads most directly align with. Launch/landing pads have been deemed as a first-order infrastructure by NASA's moon architecture. Creating these offers a base point that lunar colonies need to jump off. Following is transportation and habitation. This one is kind of obvious. Lunar landing pads offer a safe, reusable on-site landing point for continuous transportation needs. Lastly, we have operations. Completion of missions will ensure a higher likelihood of safety and completion of operations via the added safety factors of having these landing pads. It will provide safety to the crew as well as the surrounding infrastructure that currently exists on the moon. Next slide, please.
So from our RFP, C3 has lined out that for our main transport, we are using the Griffin lander. Using the Griffin lander, it will deploy our payload on the moon using the active active payload. And so the Griffin lander is 4.5 meters wide by 2 meters tall and has a 625 kilogram payload capacity and has multiple mounting options for, so it's flexible for all types of missions. And its power systems consist of a lithium ion battery and multiple solar panels. So it's able to supply our payload with 5 kilowatts consistently. Next slide, please.
Awesome. Before selecting a technology for actually creating tiles, we did a trade study looking into some of the RFPs given primarily by C3 for this competition. And additionally, we chose some things that we thought were important, including scalability and actual effect on mission. For mass and power, these are given by the competition, and you can see them weighted there. And for scalability, we tried to imagine the scale of the future lunar missions, and we wanted to create something that wasn't limited by resupply missions or other things like mining for water. Ultimately, we decided to go with microwave centering based on the RFPs we were given. We have a lot of power. We don't have a ton of mass. And with microwave centering, we can make theoretically unlimited number of tiles foregoing, stuff breaking down. Next slide, please.
So now that we had discovered that we wanted to use microwave sintering, we had to come up with a general architecture for our system. Here are a few innovative concepts that we considered for this architecture. First being the umbilical cord. So the main driver or constraint of this system is the large power draw that microwave sintering consumes. So the umbilical cord solves that problem by having a spool mounted harness that is connected directly to the Griffin lander. This offers full system capabilities, i.e. gathering, collection, conditioning, sintering, and placement, all in one single system. But the harness offers a ton of mass and adds complexity when you're trying to scale to more systems. Second, we have a mobile manufacturer. This would be a large system that it wirelessly charges via the Griffin lander and then goes out and does a sortie style construction. This would be high intensive power loads under very short periods of time. This also allows for full system capabilities in a single system, but is very limited by the mass of the battery on board, as well as the time that it takes for these high load operations. Finally, we have the stationary tile maker, abbreviated up there as STIM, and rover. This is a two-system that allows division of labor through two interconnected systems. We have a continuously powered stationary tile making system that is directly connected to the Griffin lander, and then we have a secondary rover collection system that has a small onboard battery for missions. Next slide, please. All right.
Awesome. Getting more in depth in that, here is our ConOps kind of outlining what we want to do with the stationary tile maker and rover system. So here on the left, you can see that the rover will be deployed via the Griffin lander's onboard rover ramp, and the stationary tile maker will be deployed using other means from the Griffin lander upon landing. The rover will then go out, collect regolith, and get up a store that's big enough to start creating tiles. It'll then go back up onto the Griffin lander and then use a ramp that we designed that connects the Griffin lander to our stationary tile maker before depositing the regolith into the stationary tile maker. Once the process is done, it can then retrieve the tiles and place them for testing or landing pad integration.
So after the regolith is deposited into the stationary tile system or tile maker, we go through this system. First is the reception hopper / dump reception. This is the initial entry point into the stationary tile maker, and it also acts as a storage unit in between sintering cycles. After this, the regolith passes through the vibratory screener. This is a 3-stage screener that ensures that we have the optimal granularity for the microwave sintering process. The non-optimal granularities will be filtered out via a chute to the outside of the stationary tile maker. After this, the regolith will pass into a weighing bin, which will be mounted to load compression cells that will wait until the mass target for a single tile is reached, at which point the vibratory screener will be shut off. After this mass target is reached, a rotary gate will open in the bottom of the weighing bin, depositing the correct mass for a single layer of microwave sintering. This will be enough to fill the mold and have a depth of 1 millimeter. After this, there will be a vibration sequence that is commenced by the mold itself, which is mounted to linear actuators. This will ensure that the regolith is evenly distributed along the base of the mold, which will be followed by a compaction sequence. This compaction sequence is essential to ensure that the bulk density is optimal for the sintering. After this compaction, it will undergo the array sintering process and cooling, where layer by layer, the regolith will be microwave sintered into hard block and then wait to be cooled, at which point it will go back to step 3D, another layer will be deposited. After the full array sintering and cooling cycle has been completed, the tile will be ejected in step 5, and it will be removed from the rover, or removed via the rover and tested. Next slide, please.
All right, the center properties and tile design. So for particle size and density, we're looking for low porosity results for a higher compressor strength in the tile. And we're looking for an average grain size of under 600 micrometers and a bulk density of around 2.14 grams per cubic centimeters to yield the best results when sintering. The composition, we are looking for high titanium dioxide and iron oxide
in the lunar regolith for initial heating with the microwave sintering device. And that average particle size of under 600 micrometers for the best results. And we want it to be as uniform, predictable as possible. We're aiming for the temperature range of 1,150 degrees to 1,200 degrees Celsius to maximize the compressive strength of the center tile with as minimal linear and radial shrinkage as possible. Our tile design is a modified hexagon shape with a radius of about 0.15 meters and a depth of 0.16 meters with overlapping offsets and overhangs in order to make sure that we only have one actual mold and that it can all interlock and it won't fly off.
Please.
For our landing site selection, we did a trade study for 3 landing sites, which were obtained from NASA's Artemis landing site selection. We evaluated the terrain slope, illumination, proximity to PSRs, earth visibility, and most importantly, the regolith composition. The Mons Moto Plateau site was the one that got the highest score, so we went with that one, especially because of its high time regolith dispersion and high illumination. Next slide.
All right, for our actual microwave, microwave sintering design, we decided to go with a waveguide microwave antenna. We did this because we studied up on different antenna hardware and architecture and found that it is the best way to create a controllable electromagnetic field that heats evenly over a large area. So we would be able to design a specific antenna that can be used for our shape and heat over the entire area. We are going with a 1.5 kilowatt gallium nitrate RF generator, and we're going to use 3 of them and then tune them back to 4 kilowatts for the total power output. These are 50 volts DC and have about a 63% efficiency. In order to actually see if this was feasible, we ran a bunch of simulations in MATLAB and compiled a code that did the thermal calculations, radiant properties, and a few other things on the lunar environment to determine the time and optimal area and layer height for our sintering. So you can see the outputs here, but we ended up with 1 millimeter layers, and it gave us 234 seconds per layer for a total time of 6.9 hours for the entire tile. Slide, please.
Now, moving on to our cooling system, we have separated our cooling system into a 2-loop hybrid architecture, separated with the avionics core and the RF generator. I'm going to go in a little bit in detail analysis of how the heat travels through the heat pipes, so it radiates the heat. Within the heat pipe, we will be using about 1 ounce of ammonia, which will we'll take a look into the graph on the right. It shows the flow it'll heat up from the RF generator and vaporize to the top of to all the way to the panel because of the pressure differences. And then we'll be using a caliper action method that allows the vapor to condense and go back, and it will be like a loop. And this method is essential for us to be able to continuously center without any cooling stops. And we also have thought into the idea of surviving the night. So with our avionics core, we have the panel closing using a motor, and also 2 NASA RHUs that will passively negate the heat or keep the heat within the avionics box to survive our 3 to 4 day lunar night cycle. Next slide, please.
All right, so for a quick overview of our system architecture for the STEM, some basic structural analysis lets us know that we can survive about 24 Gs, which is far more than any launch or descent will face. Additionally, it fits within our volume constraint. Then for the parts, before I get into the regolith flow, the orange box represents our RF generator electronics section. The blue box is our control electronics, and the panels in the back represent our cooling. Now, following the path of the regolith, you start at the ramp, where the rover dumps the regolith into the hopper. It then follows it through the sifter where the large particles are removed, and it is then followed into the weigh bin where it is portioned, and the volume necessary for one layer is put into the mold, where the mold is then moved over to underneath the press. After a quick vibration sequence to settle the regolith, the press will come down, compact it, and sinter it. After one sintering cycle, the press will move back up, and the cycle will repeat after gaining more regolith. Once one full tile is completed, it'll be ejected, allowing for the rover to pick it up and manipulate it. Next slide, please. This is our animation.
Slide, please.
I will now briefly go over the rover architecture. We decided on a 2-joint arm for collecting the regolith, and then some interesting things that we chose for navigation. We decided to go with wheel autometry and IMU with visual autometry correction to handle any debris that we didn't predict. And then for our power system and thermal design, we went with a Li-ion battery and then a Capstone heater to make sure we stayed low weight. Next slide.
As you can see in the video, this is our prototype that we built. As a team, I think we're very proud of it. And so we decided to go with a 3/4 scale. So that measures out to 18 inches in length by 11 inches in width. And it is completely made out of aluminum pipe, or the chassis is made out of aluminum piping and plexiglass, allowing for easy attachment of our electronic subsystem. Next slide, please.
Here's our electronics diagram for the full system. Some things to note here, we have 3 different voltages running throughout the system, including 5 volts for the control electronics, 12 volts for some of the power and motors, and then 50 volts for the RF generator system. Slide, please.
The communications system of our payload will heavily leverage the communication system and relay capabilities of the Griffin lunar lander itself. Our stationary tile maker will be placed right beside the lander and be able to connect to it just via a cord. Our rover, as it will traverse away from the lander, will connect wirelessly. Luckily, the Griffin lunar lander has wireless local area network connection capabilities, which we will leverage. The rover will have low gain antennas in order to connect to the wireless local area network and use the Griffin lander as a relay for communications. Next slide, please.
So here is our budget analysis. As you can see, the rover comes out to around 30 kilograms with a total cost of around $50 million. Our stem comes to a total mass of around 155 kilograms with a total cost of around 200 million. And then the rover power budget has a total battery pack life of 480 watts with the stem of 5 kilowatts or kilowatt power draw. Next slide, please.
For our mission risk analysis, why we identified some of the most unique and important risks for our mission and mitigation techniques for each of them. The risks were quantified on a scale from 1 to 5 on likelihood of failure and consequence of failure. All these was mapped into this risk matrix right here, which shows the arrows which represent the risk after mitigation. And since most of them fall into the green yellowish area, we concluded that most of our risks were acceptable or moderate.
Slide, please.
This is our milestones that we made. We started off the project in fall. We picked our architecture, stem and rover, and we did our trade studies with landing site, regolith processing, and then we had our conceptual design review with Dr. Shimpal, and we got good advice, and we've been working on CAD this semester, working on finalizing our tile design, and ultimately we are preparing for our PRD in May. Next slide, please.
Got about 3 minutes left.
All right, so for our biggest challenges, while ever on our track, we'll struggle with mass. Some of our technical challenges include the tile design. We needed to come up with a shape and size that struck a balance between strength and scale. We settled on that 0.15 meter radius hexagon with a thickness of 0.106. Hexagons being tileable obviously create a good option for a landing pad. But our next task was making sure it was exhaust proof from rocket gases. So we extruded the faces to create overhangs. And while this worked, it required high precision manipulation. So we rounded off the edges, allowing for them to be slid together evenly. Another issue we faced was manufacturing these tiles. Due to the nature of creating it with layers, the microwave itself needs to be able to move up and down to reach each layer. And because of the variable cross-section, it needs to be able to rotate to fit the mold. Additionally, because the regolith needs to be both evenly distributed and compacted, we need to implement a vibration and compaction system for the mold and press respectively. And then one of our earlier challenges was determining if microwave sintering was even feasible. So we created a code to model the heating of the regolith itself. And after a long process, we managed to optimize it to produce time estimates for our tiles. Next slide, please.
Over the course of the project, the main tech gaps we encountered were firstly, power access. Something like LunaGrid or a nuclear reactor would allow us to sinter tiles faster or scale up production. Secondly, more ways to test the tiles. Something like an ultrasonic sensor would allow us to determine the structure of the tile or some way to determine the chemical makeup of the tile. Lastly would be a lightweight high-fidelity manipulator for the rover that will allow us to transport the tiles and terraform the area more easily. Next slide. Right, here's our paper, autonomous construction of a lunar landing pad using in situ resource utilization and microwave sintering. Next slide.
We've already made significant progress towards a PDR. We have CAD models, animations, a rover prototype, and a concept of operations for our mission. That being said, there are still steps to take. We would like to prototype the stim itself, as well as the actual sintering process, to reach a PDR next year. Beyond that, looking towards the future and actual launch, we would like to run more tests, including intersystem compatibility tests and vacuum testing to help mimic actual lunar conditions before finally launching in 2029. Next slide, please.
So as our project has demonstrated, we have completed our objective of showing that we can reproduce these lunar landing pad tiles. These are some specs about our keynotes that you should take away from our system, and we're open for questions now.
All right, thank you. Questions?
Oh, we have one in the room.
Sorry if I missed it, but I was wondering if you considered the consistency of the regolith, and if you're just randomly collecting, what if you get large rocks, and did you think about waste and or screening?
Yeah, definitely. That's a lot of stuff we did. We didn't put much of it in here just because of constraints. But during our landing site selection, we specifically chose different alloys and material composition of the regolith. And then our actual design itself has a three-phase sifter, a vibratory sifter, and it's got 3 outlets that can shoot out while it's doing that. So it takes out the chunks so we get the right granularity.
Follow-up question. So if you're generating a lot of waste, that's something we've thought about is what are you going to do with that waste? So would you repurpose your little scoop trucks to dump the waste somewhere else?
Yeah, we haven't really thought about that, but that's probably. All right, I had thought about that.
Yeah, that's what we're.
Perfect solution.
Good, thanks.
All right, we got Greenfield online.
Hey guys, nice presentation. It was very thorough. I'm not sure if I missed this either, but did you guys talk about how you guys would deal with surface variations and yes, different surface variations as in heights and different compactness of the surface?
Yeah, so that's actually a similar thing, right? So we took a lot out, but we did a really large trade study on like the surface mapping of the lunar South Pole. And we specifically selected landing sites that were known to be flat. Obviously, we can't make that perfect, but we really tried hard. And what was it? And our wheel design is adaptable for going over moderate surfaces, nothing too crazy.
Got it. Thank you.
We got Andy online as well.
Yeah, thanks. Similar question, but a little more detailed. How do you verify tile to tile that the process is remaining consistent? Is there a onboard system that tries to measure or gauge what it looks like, or do you rely on removing the tiles and taking them to a location to test?
Yeah, that's a good question. For actual measuring on board, we do have a weigh bin for distributing, so we know it's 1 millimeter layers. And then one of the technologies that we looked into that we want to add in the future is an ultrasonic like camera system that would be inside the stem. So during the process, we can check in on things and make sure the material composition and heights and all that kind of thing are up to spec.
Okay, good answer. Thanks.
All right. Thank you, VT Luna.
Yes.
You got a picture?
Yes.
Yes.
Go one slide back too, by any chance?
Rachel, can you go? Oh, nice. Yeah. Minus points.
Thank you.
All right.
Thank you.
Got our final presentation of the day and of C3 2026 in Stellus by Embry Riddle. So you guys can get started whenever you're ready.
Instellis is not competing.
Oh, so we're done. They're not presenting?
That is correct.
All right. Jacob, do you want to say some final words to the group?
Sure, I'll take the opportunity. I'd like to thank all the students. I know you're not all here now, but certainly all the students at Goddard today for participating, for doing a great job. I mean, it is. I got comments from several people is that some of these projects they look better than some of the ICM startups. Not all of them, and they're not all bad, but it is really great work. I want to thank the mentors, the professors as well, the people that helped organize, the hosts. It's I'm kind of the face of this thing, but it is not a one-person job. And so I want to acknowledge everyone that's helped: Rachel, Alec, Uche, who ran the office hours, Andy, Greenfield. You guys came and really participated firsthand as champions, and same for Noah and Dave Barnhart and Mark Hilberger. So I think that's it. I hope that a lot of you do submit your papers to SciTech or elsewhere. I hope some of you look at NASA Ignition and submit there. I think if you have some ideas, you can apply to the guest roboticist program whenever Bo and his team get that public. It doesn't have to stop here. We see this as a pivot point, not as an end point. So thank you again. We'd love if you stayed involved. A lot of you will go work in the aerospace industry. One of the members of Virginia Tech last year, he came back as a mentor this year, and his team won best prototype. Another was working with me on getting a payload up to the space station. So this is the beginning, not the end. And I'll stop there. And if Bo or Alec or anybody else want to add something, you're welcome.
Hey, this is Bo. I don't know if y'all can hear me. I'm in the car now, but thank you all. Awesome work. Jacob, as always, great job. This is one of the crown jewels of Cosmic, I think. So So glad to have you all here.
All right. Thanks, everybody.
All right. Have a great week and weekend. In summer for some of you.